Welcome everyone to HashiTalks Build. This is one of our global events where we look to amplify you, the community, your voice, what you're building, your ideas, and your works, all on our platform here. So if you've been following us, then you know that we've got many HashiTalks events, and while they're all global, many of them are themed to local regions, with all of them being broadcast across YouTube and LinkedIn in English and the local language. However, HashiTalks Build is a bit different in that we focus purely on building things in the HashiCorp ecosystem. This means that today you're all going to hear about different tooling to build things with, interesting projects that have been built, and workflows that you can use to build your own projects, among other things. All of this being in the applications, networking, infrastructure, and security spaces. But before we go any further, we do want to invite you to participate, discuss, and ask questions in the chat. We'd love to hear from you, and our speakers will be available to answer questions on YouTube, so definitely check that out. However, we do have some community guidelines, which are pretty straightforward, that we do need you to follow. Those being be welcome, inclusive, friendly, patient, be considerate, respectful, professional, all of sort of hopefully the obvious things in 2023, but you know how common sense goes. But if that escaped you, you can review our code of conduct at hashicorp.com/community guidelines. But with that said, let's talk about our schedule for today at HashiTalks Build. So first up, we are going to hear about a new ecosystem for Terraform provider code generation from Brian Flad. He's going to talk to us about converting a real OpenAPI spec into a usable Terraform provider. And hopefully we can throw up the link here in chat with the full schedule available so that you can reference it instead of having to memorize everything that I'm saying here. But the second talk will be the AWSCC documentation journey so far with Welly and Dr. Rahul, and they're going to talk about fully automated documentation process with the AWS Cloud Control Terraform provider. So that should be pretty neat. We all don't want to write documentation manually. Well, maybe we do. I don't know. No knock on manual documentation. Anyhow, after that, we're going to get into Vault OpenAPI-based client libraries and workflows with Anton and Anna, and they're going to cover how to use the Vault OpenAPI to make Vault clients. So that should be pretty neat. The fourth talk we've got in line here is going to be Maestro. Nomad is actually an orchestrator with Daniel Bennett, and he's going to talk to us about how to create custom task drivers in Nomad, demonstrated with music, Whimsy, and MIDI. So MIDI. So I guess we're going to actually hear some tunes put together through Nomad. So that should be neat. Fifth, we're going to have building Ingress in Kubernetes and Consul with ngrok by Scott McAllister, and we're going to see how to create a custom secure Ingress controller for Kubernetes. That would have been such a mouthful years ago, but nowadays we know that's incredibly important for any of the clusters out there. And then we'll wrap up today with building Vault plugins with Christopher Swenson, how Vault plugins work under the hood and how to build them. So just trying to get a cue here from either from my producer here. Are we ready for the first speaker, for Brian to come on? Is everyone else ready for that? Okay. Well, without any other delay here, we're going to get into this first, the first talk here, a new ecosystem for Terraform provider code generation with Brian Flad. So Brian, when you are ready, take it away.
Hi everyone, and welcome to my presentation titled A New Ecosystem for Terraform Provider Code Generation. My name is Brian Flad, and I'm a staff engineer at HashiCorp, working in the Terraform ecosystem group. I've been with the company for over 5.5 years. Previously, my role was engineering lead with the Terraform provider for AWS, and now my role is on the Terraform development experience team, helping build foundational code and tooling for Terraform integration, such as providers. My team and I are very excited to discuss for the first time publicly about one of our long-term projects to better scale the Terraform provider ecosystem through code generation. This talk is intended for those building or interested in building Terraform providers. And with that, let's get started. The agenda for today's talk, we'll start with some background of how Terraform interacts with APIs. We'll talk about some of the challenges and realities to creating these integrations. We'll walk through a proposed solution and design. Then we will show a prototype and some of the next steps of the future. So let's dive into the background of Terraform and its providers. But we can first start with the context of HashiCorp products as a whole. HashiCorp products typically enable application development teams and platform teams to work across a broad range of infrastructure services. Today's topic, though, is about Terraform itself. Conceptually, Terraform provides workflows that enable practitioners to write a declarative configuration which describes the resources they wish to manage in their infrastructure services. These might be virtual machines, disks, or other infrastructure components. This happens by Terraform reading the configuration, generating a graph of operations, then calling an API which actually performs those operations in the infrastructure service. The concepts in the middle represent the interface between the practitioner and their desired infrastructure. This is where the magic happens with Terraform. Now, creating and maintaining a single product or code base that would implement all potential APIs would be quite difficult. There are thousands of infrastructure services available today. To enable better extensibility, Terraform has the concept of a provider plugin. Its role is enabling configuration which ultimately calls those services. Providers are a collection of managed resources and data resources. Managed resources handle a single infrastructure component with a full management lifecycle such as creation, updates, and deletion, while data resources are read-only sources of information about infrastructure components. Ideally in this design, a provider is focused on a single API, and resources are aligned with the terminology of the service. This is intentional as it offers benefits to both practitioners and developers of these integrations. Only a single domain of expertise is needed, the service itself. For practitioners, it also means that there is a centralized handling for connectivity and authentication to a service. For developers, it also means that there's no need to create abstractions for multiple resources or across services. Those abstractions can be handled elsewhere through Terraform configuration functionality, such as Terraform modules. If we look at the diagram again, it still appears to be a little ambiguous. How exactly does a provider implement both Terraform concepts and the logic to call APIs? If we expand the diagram a little, there are some new pieces to the puzzle. There are software development kits, or SDKs, that relate to both Terraform and the API. Developers combine these two SDKs to create the provider code. Let's talk about the Terraform side of this first. A Terraform SDK is the provider code component which is responsible for building logic for Terraform's concepts. Between Terraform and providers is a protocol which defines all the operations and data that can pass between the two. Collectively, these protocol operations are bundled together into a higher level abstraction created by the Terraform SDK, such as the provider's definition of a managed resource or data resource. On the other side of things, specifically the data, the Terraform SDK bundles together higher level abstractions of what data is and how it gets represented in code, whether it be the concept of a schema definition, which describes the structure and types of data, or a type system to read and write that data. If we look a little deeper into what goes into developing a provider resource as it relates to the end goal of communicating with an API, there are some more important concepts. There are the expected bits, such as defining a unique name for the resource, but the more interesting bits deal with defining a schema and operational logic. A schema does a lot of heavy lifting for a resource. It describes a shared shape of configuration, plan, and state data for Terraform. It also must account for any oddities or normalization that might be required between the naming and shape of a desired configuration for practitioners, API request data, and the API response data. On the operational logic side of things, there's the overall mapping of API operations to whatever resource is being created, read, updated, or destroyed. Then within each of those, there's the reading of Terraform's schema-based data, converting it to the data types used by the API SDK, actually calling the API operation, then any necessary conversion and writing of Terraform schema-based data. HashiCorp today offers 3 SDKs for Terraform, as shown here. Terraform Plugin Framework is the most recent iteration of Terraform SDK, which supports all of Terraform's provider functionality available today, and is recommended for all new provider development. Terraform Plugin SDK is the prior iteration, which works okay and is well used across the ecosystem. However, it's lacking some functionality and imposes certain provider behaviors which cannot be easily controlled. Last is Terraform Plugin Go, which generally most developers do not need to know about, but it is a lower level abstraction and can be helpful in some very advanced use cases. In addition to the SDKs themselves, there are a lot of HashiCorp and community-owned projects which can help simplify provider code, automate documentation, and run testing. One of my favorites in this list is Terraform Plugin Mux, which can be used to iteratively migrate a provider code base from Terraform Plugin SDK to Terraform Plugin Framework. In any event, that describes the Terraform side of provider code. Let's switch our attention to the API side of provider code. Much like Terraform having an SDK that codifies its concepts, APIs have a similar notion. API SDKs are a native programming language interface to the API. These generally exist because it would be a huge burden on developers wanting to communicate with an API if they needed to take generic programming language constructs, such as an HTTP client, and manually develop all the necessary parts and bits to successfully make API calls. These API SDKs typically involve an API client, functions for calling API endpoints, and types for all the request and response data. So that describes some background on the provider code and SDKs that are used to develop it. It might be helpful now to take this diagram and flip it on its side. This now describes the manual provider code development workflow. A provider developer combines the available concepts of their Terraform SDK and API SDK to write provider code. There's one last piece before we move forward, though. Some APIs are developed using an API specification or API definition. This can generally directly influence the design of API SDKs and can be used to deploy an API. API specifications, or more generically, interface definition languages, are ways that API developers can automate some of their work. They typically provide their own abstraction concepts, behaviors, data modeling, and potentially API SDK generation. Some examples of API-focused IDLs include OpenAPI specification, protocol buffers, Smithy, and TypeSpec. Each of these has its own terminology, concepts, and project goals. But if we look back at our manual provider development flow, you might notice that there's an interesting disconnect between those API specifications and provider developers. Now, it'd be great if every developer could easily create and maintain a Terraform provider for every API, but let's talk about some of the realities or challenges that HashiCorp has noticed as the ecosystem has grown. The first reality is that APIs support more than just Terraform providers. Many API services support a multitude of API clients, where a Terraform provider is just one integration. This has some potentially unexpected consequences, though. The API may define components which don't align to Terraform's resource model, such as implicit resources that cannot be created or destroyed, only updated. The API may define operations which affect multiple resources. The API's data handling may not match Terraform's data model, which has consistency rules such as state values must exactly match its configuration value. Also, an API may not define errors well enough for Terraform's purposes, such as returning an unauthorized error instead of a missing resource error. Any of these are a barrier to a high-quality Terraform provider today. A second reality is that developers support more than just Terraform providers. While there are dedicated provider developers in the ecosystem, it is generally uncommon. With that perspective, there may be developer unfamiliarity with Terraform concepts, its SDKs, the Go programming language which those SDKs are written in, and potentially other provider quality features such as documentation and testing. Any of these are also a barrier to a high-quality Terraform provider today. Another reality is that the existing provider ecosystem is both broad and deep. For example, there are over 3,000 providers in the public Terraform registry and many more in private Terraform registries. Out of those, there are over 250 providers in the public Terraform registry, which are participating in the Terraform integration program. There is an amazingly wide variety of services and the technology industry represented by these providers. This entails everything from cloud computing, networking components, database management, and so much more. Did you know that you can order pizza through Terraform? That's a story for another time. But if you look at the raw metric such as provider downloads, it's measured in the billions. Clearly, providers are giving practitioners some value. Another interesting aspect is how deep some of these providers are integrated with their services. The AWS, Azure, and Google providers, for example, have almost 4,000 resources under their umbrella. Wow. Another fun reality is that Terraform provider code is often repetitive. However, repetitive code is both a feature and a bug if we dive deeper. Consistent and repetitive code can be boring, but it does tell us some information about our domain. One way to look at it is that APIs tend to follow certain conventions, which is great for consistency. It's less great when code is being manually developed, though, and especially when there's external contributors. These can cause issues such as inconsistent schema definitions, where developers may omit certain attributes or miss certain documented validation behaviors of an API. Inconsistent data handling, where developers may duplicate or incorrectly modify similar code. Inconsistent error handling, such as missing resource state removal on read when an API returns that type of error. And other code duplication, where introducing functionality is considered more important than the maintenance burden. Out of that list, though, it is especially important to call out that valid schema definition and data handling is critical to a successful resource implementation, but it also requires a high amount of effort, and a lot of that effort tends to be replicated or duplicated code. Now, there are certain solutions available to provider developers dealing with these code consistency issues. Sometimes it's possible to create code helpers or packages to deduplicate the code, as with any programming language code. Another option is implementing static analysis or linter tooling that can enforce coding standards and guardrails. In some cases, provider developers may have even gone down the road of code generation. You'll note, though, that all of these solutions tend to be very specialized. Which leads us to our last reality to be discussed today. Specialized code and tooling does not scale. However, specialized code and tooling is required to scale. That last point there is an interesting dichotomy. Most solutions we have seen in the ecosystem have tended to be for specific use cases, such as provider code generator included with a single provider code base, based off of that specific API's conventions and behaviors baked in, instead of a more generic solution that could help the ecosystem more broadly. What if we could reduce or solve these challenges for developers by introducing a more generic solution? Before we try to design that solution, though, let's discuss some of the proposed requirements for that solution. First up would be adaptability. HashiCorp has a long-running adage about its products promoting workflows over technologies. This feels highly applicable in this case. For starters, the technology ecosystem is constantly evolving and improving. With that evolution in mind, some of the relevant details that would affect our solution here is that both API and Terraform concepts, development practices, and tools will change over time. It may be easier to think about this in the sense of technologies or functionalities, but the development model changing over time is likely more pertinent or likely to occur. For example, with a company that maintains its own provider, lowering the maintenance burden may become a business priority, which may lead to more desire for automation than before. Another piece of this is that it would be unreasonable for one technology, whether existing or created as part of this solution, to solve all the issues forever. The solution will need to evolve with everything around it. A next requirement would be extensibility. The existing provider ecosystem is done well because it is extensible. There's not one centralized group of provider developers making the ecosystem a success. Additionally, many providers and provider tooling is also open source, which means that there's an accessible corpus of private art, example code, etc. when encountering a development situation. An extensible solution should also account for foundational blocks being more helpful than a prescribed solution. With foundational building blocks, it is still possible to build a specialized solution. It may be more effort initially, but it will pay dividends in the long run. Another aspect that is that designing an interface can reduce the required knowledge on each side of the problem domain, while also increasing consistency. And this is due to the introduction of a shared language. Last but not least, the solution should account for the fact that designing an interface can be generic while also enabling specialized use cases. This kind of ties up to what we were talking about before. A final requirement would be usability. As mentioned before, the provider ecosystem and broadly speaking, the API ecosystem already exist. A solution should account for both new and existing provider use cases. Or more concretely, this means lowering the barrier of entry for creating new providers and reducing maintenance for existing providers. The solution should also account for new and existing provider developers. This means lowering the barrier of entry for new developers, such as making it easier for them to be more successful, and enabling existing developers who provide more practitioner value. Additionally, the solution should account for the existing technology gap we already discussed earlier, where API specifications have a wealth of useful information. Now, with our proposed requirements ready, let's start designing a solution around those requirements. This proposal is based on the idea that we can design scalable code generation that meets developers where they're at. If you haven't guessed already, the proposed solution can be summarized as creating an interface. It will also include some other starting pieces. From a high-level view, the following workflow is being introduced. On one end of it, there is various sources of information, and on the other end is provider code. In the middle is our generic interface, and it is surrounded on both sides by specialized tooling on that interface. Now, while these diagrams will show the individual components of the workflow, I do want to note up front that these components could be bundled together as desired. As shown here, there's nothing preventing the creation of a single developer tool that simplifies the process from source to generated code. If we take a deeper look into how these components might operate, you'll notice that we have some of our components from before. A source generator or converter may accept API specification and/or API SDK information. On the other side, the provider code generator is based on a Terraform SDK. Currently, we are going to call the interface the provider code generation specification. I'm sure our marketing folks could improve that naming. Anyway, it's designed to be a versioned interface between one or more sources and one or more consumers. It's intentionally programming language agnostic, source agnostic, and consumer agnostic. It does, however, need to be tailored for a problem domain, which is specific for Terraform providers. Also, while it initially may be focused on code generation, it could theoretically be extended for other use cases as well, which I'll mention shortly. The specification information can be filled in with one or more sources. One valuable source would be an API specification, such as OpenAPI, since typically the API SDK information can also be determined at the same time. If that's not available, another potential source might be parsing the API SDK code itself, which could be very tricky, but technically possible. A helpful source might be a developer scripting or manually filling in the specification information. This might sound like moving the manually developed code problems around, but we'll discuss some of the valid reasons for this. And if you're into the current technology hype, trends, maybe a large language model could help. Also, maybe somebody will make a website for designing a provider. Plus potentially more. Don't let this list stop you. On the flip side, the specification information can be handled by one or more consumers. The main focus is provider code generation initially, but the specification could also help with documentation and testing generation in the future, if that makes sense. Now, from the developer perspective, each one of the components can become a configuration point. Maybe the source conversion generates all potential resources, while only some are desired in the provider code. Maybe the source conversion is not fully correct or includes generic API schema descriptions instead of those tailored for provider documentation. A developer might also be stuck in a situation where there is no source conversion available, only the API SDK. In this workflow, the developer can opt to fill in the specification information. This affords them the ability to get consistently and correctly generated provider code. Especially in larger providers, this might be the starting workflow for introducing the code generation to begin with. And finally, in an effort to be the most flexible, this solution does not prevent the manual code development workflow we discussed initially. While this should hopefully diminish over time, some resources may not work well at all with code generation. This workflow should stay out of the way in those situations. This all sounds great in theory, but let's discuss the proposed solution with real-world workflows and data. To do this, we can take a common scenario and try to provide immediate developer value with a prototype. The main focus of our prototyping effort was schema and data handling, since it could provide the most immediate value. Starting from the high-level workflow, we opted to swap out each of the loosely defined components with real-world implementations. These included OpenAPI specifications as the source, the creation of an OpenAPI to provider code generation specification converter, and the creation of a Terraform plugin framework provider code generator. For the OpenAPI side, we created a CLI and Go module that was able to validate and parse OpenAPI specification and generate the majority of schema definitions and validations. Since OpenAPI does not have Terraform's concept of a resource, the prototype accepts a configured Terraform resource mapping of the API paths and operations that should be associated together in a single resource. For the provider code generation specification itself, the prototype supports the concepts of provider, managed resource, and data resource definitions, schemas within those, all schema types and nesting, associating API SDK types to the schema types, and various other schema functionality. For the provider code generation side, we created a CLI and Go module that creates Terraform plugin framework code. Its usage can be tailored, such as individually selecting what resources and what parts of those resources to generate. The main functionality supported was generating schema definitions and data model types. To briefly see some of the prototype artifacts, here's the pet store example OpenAPI specification, which defines an API with endpoints for managing pets and orders. In our prototype testing, we also used real-world OpenAPI specifications from our friends at GitHub and Scaleway. Here's the prototype OpenAPI conversion configuration, which defines the mapping of API paths and operations to Terraform resource operations. The OpenAPI converter collected all of the API request parameters and API response contents to create a merged resource schema in the provider code generation specification. Then the framework code generator was ran, and it generated a Go code file with a package, name, imports, and schema code. Hopefully you can see the direction we're heading. So, what are our next steps here? We are targeting a technology preview release of our prototype components for HashiConf later this year. Before then, though, we'd love some early feedback from partners and customers. If you're a part of the Terraform integration program, please reach out to your HashiCorp Partners or Alliance contact for additional information. If you're a customer developing private providers, please reach out to your HashiCorp account manager. Thank you for watching and hope you enjoy the rest of the sessions. Please reach out with any questions. We would be happy to answer them.
Thanks, Brian, for the deep dive into the providers and all the great stuff we've got going on to there. And I like how he gave a tease as to what's going to be coming up to a HashiConf, which, speaking of which, is going to be taking place October 10th through 12th in San Francisco this year. And registration is actually now open. And you can visit hashiconf.com for more detail. For more details, I can see the little screen scroller there at the bottom. But also, we're going to be giving away a complimentary pass and 3 discounted passes to HashiConf. That again is going to be on October 12th through 10th through 12th. And how do you win? Well, we should have we have a little banner here under my big head to where you can go to try and get one of these wonderful passes. That being said, in order to be eligible, you do have to be registered for HashiTalks Build, which hopefully you are, and if you're here. But I think that is all we needed to say on that. Thank you again, Brian, so much for the dive into Terraform provider code generations and the providers in general. Obviously, without those, the ecosystem wouldn't be what it is today. We wouldn't be able to pull in so many other different APIs and therefore services and external platforms into our community. Okay, so that's going to bring us to the second talk that we have today, which is the AWSCC documentation journey so far with Welly and Dr. Rahul. And they're going to walk us through, again, automated documentation process. And while this will be for the AWS Cloud Control provider, or really any Terraform provider, and if you're just curious about automating the documentation process in general, you're going to benefit from checking this out. So whenever y'all are ready.
Hello everyone, welcome to the HashiTalk build. I'm going to share with you about the documentation journey for AWS Cloud Control Provider. We have a lot to cover and I'm sure you have a lot of questions, so let's get started. My name is Welly Siauw. I'm the Principal Partner Solution Architect here at AWS. Today, I'll be joining with my colleagues and friends, Dr. Rahul Gaikwad. He's a lead consultant at AWS. I'll start by setting some stage, and then Rahul will join us later for the deep dive demo. Now, let's imagine this. You read the AWS news announcements for a new service, and that's happened on Thursday morning. And then you found that the resource or the data source is available in the Terraform region that's available on Tuesday afternoon. Then no more waiting for someone to open GitHub issues, thumbs ups, or maybe making a pull request. At AWS, I had an opportunity to be part of various AWS service team launches, and I know exactly the level of effort made by various teams, including service team, the providers me, and also the Terraform team itself. And for some of you, you have contributed to the AWS provider, so you know exactly what I'm talking about in here. And we make a lot of progress on this front, and I'm very excited to share some of the new approach and progress we made today. So for that, first of all, I want to introduce you to AWS Cloud Control Provider, or we call it AWSCC. It's an auto-generated, fully auto-generated Terraform provider. It provides you access to provision all of the hundreds of AWS resources that is currently supported, and all using single consistent API. The AWSCC automatically syncs with the registry, Cloud Formation Registry, and it uses the Cloud Control API to generate that resources and the schema and handlers. That means automatically you get access to those resources, typically within days, sometimes within hours. So, are we there yet? Is this the promised land? Now, the fully automated workflow in AWSCC begs the questions. Are there something else for us as part of the open source contributor to contribute? And the spoiler alert is yes, we are not there yet. We have plenty of other innovations to work on. So stick around and we're gonna learn more. But first, it would be a big mistake not to recognize the big key role played by all of the Terraform contributors. Thank you to you all. The fact that we have such a healthy and engaging community is a big asset that we all play a key role on. AWS providers is on track to hit 2 billion downloads, and that popularity is testament to all of the effort made by the contributors and also by the community. So switching the gear back to AWSCC, maybe the first questions that come up in your mind is, what is AWSCC? Why I never heard about it? What can I do? So let's take a step back in time and rewind a bit. It all started with motivations. We all want to deliver new business value. We want to tackle hard problems, and for that, you need to unlock access to innovations. With hundreds of AWS services, that momentum is just keep rolling faster and bigger. Take a step back. More than a decade ago, AWS launched 80 significant features on that year. If you fast forward to 2021, after a decade, that number is actually 3,000 features and more. Last year is 2022. We had 3,352 significant features that was launched. So we asked ourselves here at AWS, how can we help our customer gain access to these features? And we know that they want it fast, they want it now. And the signal is very clear. Our customers, we want to use Terraform to provision the infrastructures. So let's take a sample of this simple SEL configurations. Now here I have an IAM role, VPC, and also an S3 bucket. In AWS, you often hear us about 2 pizza team. We operate lean and fast. So that means each of these services has its own API endpoint, has its own create, read, update, delete, and list operation, or we call cradle, create, read, delete. And then each of those APIs also has its own schema, handlers, and also the error code. So take example of that previous SEL configurations, the binary of Terraform handle the parsing, initializing providers, and validate the SELs. Then the provider act as a plugin that interact with the external API. In this case, are the AWS services. And because they are each in terms of the implementations, that provider, AWS provider, act as a translation layer between the Terraform and the services. So when a new feature services is launched, then we repeat the process, the API spec, open a GitHub issues, create a pull request, running a test, review the request, and then merge and approve, and etc. You're all very familiar with this. Now, you can imagine this can take days, weeks, and sometimes months, especially for new services. Now imagine we don't have to do that because imagine you don't need to use, well, imagine that the Terraform provider don't have to interact with each of individual services. Now imagine it can interact with just single API that consistent with the consistent cradle essentially. And this is what led the development to the AWS Cloud Control API. And it acts as that consistent cradle API that's supported by the other AWS services. And at the same time, HashiCorp teams also developed the AWS Cloud Control Provider, or the Terraform provider for it. So great stuff, sounds great, very promising. But again, what is Cloud Control API again? You might ask. Okay, next couple slides, I'll try to explain what is Cloud Control API without saying Cloud Control API. So first, imagine you have this, you just need to remember that create, get, update, delete, and list. And because there's only 5, I don't have to map the AWS SDK for each of those services because all services use the same 5 command in here. Theoretically, I can get consistent response and also error handling from this one API. So that's the first design principle. Second, imagine you have consistent schema for that resource definition that you try to hit through that 5 API calls. Basically, that's the standard specification of how you develop resource in AWS, like properties of the resources, the data types, for example, which parameters are required, the identifiers, and etc. In theory, if I have consistent schema structures, then I can programmatically scan that schema to map all of my resource attributes. So also means that I don't have to inspect the resources for each of the AWS services individually to make sense of their schema. I can just go to one location. So then that leads us to the third component. And that is the place to find the schema at the registry to publish the schema to the external party. So if you try to put that 3 design components in practice, we start with the registry. This is the CloudFormation registry, where each services, when they onboarded a new feature or new services, they publish the schema into this registry. When they develop new services, it's mandatory for them to include that schema prior to the service GA or the service launch. And then we download this registry. There are multiple endpoints provided by the registry to download the schema file. And of course, we do this programmatically. But in case you're curious, just Google CloudFormation registry schema downloads, and you can find a link to actually inspect the file. Now then, here's the cool part. The AWSCC provider team is done by HashiCorp team in here. They have a cool code generation tool. It runs weekly. It downloads the schema file, and then it doing the diff to find what's the new resources. And when you find it, it reads that resource provider definition schema to understand what are the attributes of the resources. Again, remember we have only 5 API calls to remember: create resources, define the schema, and etc. So as you can imagine, some resources can be complex, right? It could have nested attributes, lists, maps, map of strings, map of lists, min-max values, and etc. So this code generator takes that into all accounts, and then it generates the provider handler for the resources. It has the data source as well. It provides acceptance tests and also the documentation. So from here on, the build process complete, new release is made available. You go and update your provider, AWSCC provider versions, and then you can start using that resources in your SEL configurations. So very, very cool. There's a ton of work done by both HashiCorp and also AWS to make this happen. This entire process is way more complex than what I can explain in here in just couple of pictures. In fact, it may warrant its own HashiTalk discussions. But for now, let's just refocus ourselves on the last pieces in here, which is the documentation. So I explained to you what is Cloud Control API without saying Cloud Control API. And also earlier I mentioned that the AWSCC code generator also generates the documentation for you that you typically saw in the Terraform registry. So if that's the case, then why we are here today in this HashiTalk sessions, right? The documentation has already been generated as well. But let's take a look. First, I want to take you to the familiar registry documentation for AWS standard provider. Now, when the contributor wrote the resource provider, they add practical example how to use the resources. Over time, these examples are getting better and better with complete example that you can almost copy paste to your configuration. And on top of that, the argument or labels description is included, often with great practical example that provide pro tips, call out for edge cases, rough edges, and best practice as well. And now if you kind of bring it to another example, very familiar page, but a little bit barren. And this is the same resource documentation, but this is in the AWSCC provider documentation in the Terraform registry. Yeah, so it doesn't take trained eye in here to notice. We don't have practical example in here. And for you, maybe you're pro users, you don't need example, you can just kind of configure it. But for many practitioners, we often hear this is the first frictions in terms of using AWSCC provider and arguably any provider. So we are human. We are trained to mimic what we can learn from the word. And in the absence of example to mimic, then the friction essentially filling the gap. And you also notice the argument description is quite bare bone. I took a very extreme example in here, but just to illustrate the problem. But this is consistently a problem that we are facing in this particular particular topic. So why is that? It's because the documentation is rendered from the resource provider schema in the AWSCC repository, which in turn actually come from the same resource in the CloudFormation registry. And this is what that resource schema looks like in the CloudFormation registry. Skip the other part, just kind of focus on the pieces that I highlight in here, and you notice that there is no descriptions about these properties. And that summarizes the problem statement. First, we need a practical example. We also need to enrich the property descriptions. We know that we need to improve, and there's only better result from here on. And look at this example in here. This is for the OM link resource. By the time we finish with this HashiTalk, I encourage you to go to Terraform registry, look for it, and see what's the result on the AWSCC. So we are making progress. So switching gear, a quick deep dive. I want to introduce you to the Terraform plugin docs, also called the TF plugin docs. If you're a provider developer, you probably are familiar with this. And maybe for you, AWS provider contributor, this may be a little bit new. The Terraform plugins is capable of this Terraform plugin docs capable of generating documentation in the Markdown format. It takes SQL file, say this example TF, and then it render it with the Markdown example templates, and along with that, it also generates other resource properties. It then export this schema information from the provider. It can run that by using this Terraform provider schema command. And the Terraform plugin docs also generate both of the resource and the data source documentations. My colleague Rahul will demonstrate how this works later, but just a very quick sneak peek. Here's the just regular Terraform example file that I showed you earlier. And then this is the Markdown templates. Rahul will go more deeper into these Markdown templates and how they use. And then finally, this is the Markdown outputs, which then been rendered in the Terraform registry. All right, so that's just a quick sneak peek. In the next session, we'll dive deeper. Rahul, please take it away.
Wow, that was amazing. Thanks, Welly, for sharing your valuable insights. Let me take the baton for a moment and demonstrate practically on what you just said. All right, it's a show time. My name is Dr. Rahul Gaikwad. I am a lead DevOps consultant at AWS. Today, I would like to demonstrate how you can contribute to Terraform AWSCC provider documentation. Before I start on demo, I would like to share one of the customer use case. In 2022, I was working on one of the customer engagement at AWS, where customer wanted to deploy AWS Fault Injection Simulator Service, that is FIS, using Terraform as infrastructure as a code. When I looked for a Terraform AWS provider resource, I could not find any because FIS service was quite new at that time. Then I researched and I got introduced to AWSCC provider where I could explore and deploy FIS using AWSCC without any further waiting on AWS provider. Now, let us switch the gear and deep dive into how each and every one of you can play a vital role in contributing to the AWSCC documentation. I will also explain the contribution steps and give you the opportunities to make you an impact to the HashiCorp and AWS community. Imagine you are an aspiring contributor and ready to conquer the world of Terraform AWSCC provider. But wait, how and where do you start? It's a multi-step process to contribute to the AWSCC provider documentation. Firstly, I will explain 4 steps at a very high level, and then I will deep dive in each step. First thing first, we need to choose our weapons of choice. I will talk more about tools and setting up your dev environment in upcoming slides. Once you set up your playground, identify the available AWS resource to write an AWS example. You may want to deep dive to the AWS resource before you actually develop your own example. There are plenty of options available for you to explore and learn about that resource. Now, suppose you all learn about that AWS resource and understand how it works. Now, here it's your time to get hands-on and build a new AWS example. Alright, at this stage, you have finished your example with your coding and extensive testing. Once you are satisfied with your example, confident in your test, and ready to share your contributions with the community, you can submit your pull request. And that's it. You just impacted a broader community by submitting your great contribution. Now, let us deep dive in all these steps one by one. First, you need to set up your dev environment. You can choose your favorite development environment. My favorite development environment is Amazon Code Catalyst. Someone may ask, why Amazon Code Catalyst? As developers, we know that our core capabilities lies in creating innovative and efficient code that solves business critical problems. Yet, we often find ourselves distracted by the complexities of setting up and maintaining our development environments. One of the key advantages of this setup is that it comes with a pre-installed dependencies, eliminating the need for a manual intervention. Whether you love using Visual Studio Code, PyCharm, IntelliJ, or any other IDE, Amazon Code Catalyst supports all of them. First of all, you wanna pick a resource, you can go to the AWSCC registry, search and browse for any resource that you are interested in. We recommend you to explore the resources and pick any available resource which you feel confident. Once you pick up the resource, I highly recommend you to deep dive in that resource. You can either go through the AWS documentation to understand how that resource works, or you can also check AWS Cloud Formation documentation to learn about that resource schema and their attributes. Before you start on AWSCC example, you can also visit the Terraform AWS provider documentation and their examples. You can even demonstrate your creativity by writing a multiple examples, including basic example and advanced examples covering specific use cases. After you learn about the resource, you can build your own test example using Terraform AWS provider. It's important to understand how it works with the Terraform AWS provider. Then it will be easy for you to write an example in AWSCC provider. You should explore the resource and their attributes by running Terraform plan. I encourage you to do extensive testing by running Terraform apply. You will understand how the resource gets provisioned using Terraform AWS provider. Once you understand how AWS resource works with the Terraform provider, now you can deep dive on the Terraform provider AWSCC repo and you can explore that repository. Try to understand that repo structure, go through the README, some existing examples, and earlier PR contributions. There are many directories in here. For now, pay attention to just three. The first one is example/resource directory, templates directory, and the docs directory. Then you need to fork the Terraform provider repo in your own GitHub repo or GitHub org. You should clone your forked repo in your dev environment, which you set up in last stage. Once you set up your dev environment, you can clone your repo and you should create a new feature branch. You can follow these naming conventions for creating a branch where D represents the documentation. In this step, you can start writing your example in conventional path. As you have already explored a repo structure, you can easily understand that your example should be stored under the example/resources folder with your resource name. Once you completed your example, you need to create markdown templates where you define some high-level description. The templates provides a couple of useful contexts that you can use out of the box. For example, .name, .name of the resource or data source. .type, either resource or data source. .description is a description of resource or the data source. Also, notice in here, I get creative and I put a 3 examples for different use cases as shown. You need to store your new template in the conventional path. For resource, you need to place under the template/resources/folder. Also, pay attention to the template file name. We encourage you to keep the consistency format. For simple use case, service name hyphen resource name dot md dot tmpl. for multiple example service name underscore resource name underscore use case slash example.md.tmpl. Then you do a linting, making sure you don't make any typos or unintentional errors. Then you do a local test by running a make docs. This is a creating for actual markup documentation from earlier example and markdown templates. Then create a draft pull request with work in progress at the beginning of title so that others can understand that you are still working on it. Once you are ready after extensive testing, you can remove that WIP tag and submit for review. Once you submit it, it will go through the auto check process. If any check fails, you need to troubleshoot, fix, and recommit. Once all checks pass, reviewer will pick up your contribution and provide the feedback. If all look good, reviewer will provide his comments and he may approve your PR. That's it. Next is a call for action. Alright, this is now the end of the presentation. We would like to share a couple of key takeaways for you. If you are interested with what we are working on here, please join us and start contributing. If you are brand new to AWSCC provider and want to learn more, here is the examples that you are looking for. We have so much more to do. Let me share a couple of things in our mind right now. First, we have seen increase of adoption of AWSCC, and with that, we also started to look for the automated solution and fixing it. If you see some issues with AWSCC, don't hesitate to raise the GitHub issue. Second, we are also actively looking for the active contributor. If you have any idea, open a future request in the AWSCC. We want to hear your feedback. Lastly, since Gen AI is a hot topic, perhaps someone from the audience may want to leverage Gen AI for the AWSCC. We'd like to hear your feedback and your experiment as well. Thank you so much for your time. Enjoy the rest of HashiTalks conference. Thank you. Bye.
Thank you very much, Welly and Rahul. That was a great presentation, and it's been neat to see the AWSCC provider evolve because obviously, I work at Hashi, so I've gotten to see the process. But it was also, I love the attention to the documentation, to the practitioner, how that's going to be improved and how that's going to help pretty much all future development going forward, both from a speed standpoint, right? And I guess that's the main one, speed in both the you being able to use it from a documentation standpoint and access to the services as they come out. And it's also been interesting that we've kind of stayed on this theme of using an API spec, an open API spec to generate documentation without having to do so much manually. And interestingly enough, we're going to kind of stay on that theme for the next talk here from Anton and Anna. This is going to be on Vault Open API-based client libraries and workflows. So we're going to see this theme continue on and how to use the Vault Open API to make Vault clients. So when y'all are ready, we'll go ahead and put those speakers on.
Hi, my name is Anton Averchenkov. I'm an engineer here at HashiCorp working on the Vault DevX team. And today I'll be presenting with my teammate, analyst Diroff. We'll be talking about Vault OpenAPI-based client libraries and workflows. In particular, we will first cover the basics of the OpenAPI specification. We will then discuss how OpenAPI is generated and used in Vault, and how you as a plugin developer can improve the OpenAPI spec generated for your plugins. And finally, we'll showcase two new OpenAPI-based client libraries that we've been working on, Vault Client Go and Vault Client.net. All right, let's begin. So first, what is OpenAPI and why do we need it? OpenAPI specification is a language-agnostic industry standard for declaring and describing your RESTful APIs. It's a very simple YAML or JSON file that is readable by both machines and humans. But it's incredibly useful and powerful. It can be used to generate both client and server code in dozens of different languages. And it can also be used to generate documentation or even automated tests. It is currently maintained by the Linux Foundation as part of their OpenAPI initiative. Here's what a typical OpenAPI file looks like. This is a YAML example. It's essentially a collection of path objects, each of which has one or more operations, such as post, get, delete. The path and the operation can be translated directly into a REST call, and the rest of the elements can be easily mapped into the code. So for example, the operation ID is typically translated into the method name. Okay, let's see how OpenAPI is used in Vault. Vault is a bit unusual in its usage of OpenAPI. The spec is generated dynamically from the loaded plugins rather than having a static source of truth file. You can access Vault's API spec by calling this internal endpoint. Alternatively, you can run gen OpenAPI.sh script, which loads all built-in plugins and calls the endpoint for you. It is also worth mentioning that Vault's OpenAPI spec is not yet officially published, but we are very close to publishing it. So within Vault, it is used by many UI components. It's also closely integrated with the help text. For example, you can call Vault path help to fetch OpenAPI-like description for your given path. And most recently, and most importantly for this talk, we have started using the spec to generate two new OpenAPI-based client libraries, Go and C#.NET one. Once we release the spec, more libraries will soon follow. Alright, let's hop into the demo. I'm going to show how we can generate and modify the Vault OpenAPI spec. I'm in the Vault directory. Let's take a look at gen OpenAPI.sh script. As I mentioned, it's a very simple script. We start up a dev instance of Vault, then we mount all the built-in plugins. And at the end here, we call OpenAPI endpoint and redirect the output to OpenAPI.json. Let's run it. So it generated a fairly large file, almost 50,000 lines of code. Inside, it looks like a fairly typical OpenAPI spec file. Now, let's assume I wanted to modify the OpenAPI output for KVV2 read configuration request and its response structure. I happen to know that the plugin used to generate this is Vault plugin-secrets-kv, and I already have it cloned. Let's take a look at the path-config.go, which is where our endpoint is declared. This is a fairly typical path declaration. There is a regex pattern followed by display attributes, which allow us to modify the OpenAPI operation ID. Below you will find the request fields and a list of operations. The read operation is the one that we want to modify. Let's change the operation suffix, which will modify the operation ID. I'm going to add -demo at the end. And for good measure, I'm going to modify one of the response fields max versions to be max versions underscore demo instead. You'll notice right away that we broke some tests. This is expected because we're calling a few test helpers to validate that the responses match the declared response schema. Since we've changed the schema, but not the actual response, the tests alert us that there is an inconsistency. To fix the test, you would simply adjust the response names to match the schema, but we don't need to do that now. Instead, let's build the plugin and load it into Vault so that we can see the new OpenAPI schema. There are a couple ways of doing it. For built-in plugins, I can just use a replace directive in my Go mod to link against my local version of the plugin. But I'll show a slightly more complicated method that should work for any plugin, not just the built-in ones. In order to do that, we need a regular non-dev instance of Vault. So luckily I have a script here for that. I'm going to modify our gen openapi.sh and replace vault server-dev with vault server-config. And then I'm going to copy the rest of the code here. This code block first initializes our local vault. It then unseals it with the unseal key, and then it logs in with the root token. This is not a very secure way, but we're using it just for the local OpenAPI generation, nothing else. Let's also copy the Vault config file. As you can see, it's very minimal. And let's run our gen openapi.sh script again. We should expect the same output. Oops, it looks like there was a permission issue. Let's try to debug it. Ah, right, I forgot to update the root token when curling the OpenAPI endpoint. Let's update it. Okay, much better. So to promote our changes into OpenAPI locally, let's actually load our KV plugin. To do that, I'm going to create a My Plugins directory under the scripts where our test vault is run. And I'll copy the plugins binary into it. We'll also need to mark My Plugins as a trusted plugins directory in Vault's config. And finally, we want to register the plugin. The plugins README here has the exact command. Let's copy this command. We'll also need to generate a SHA-256 sum of the binary. This SHA-256 is used to protect against rogue binary injections. Okay, we're all set. Let's back up our OpenAPI.json. and run the script again. As you can see, the OpenAPI spec was modified to reflect our changes. We have the max versions demo and the KVV2 read configurations -demo operation ID. And just to summarize what we did in this demo, we modified Vault plugin secret KV plugin, ran the test to discover the validation failures, built it, then modified our OpenAPI script to start a real non-dev Vault instance. We registered the plugin's binary, and finally we ran the script to see a new OpenAPI.json with slightly modified fields. For the official release of the OpenAPI spec, we're planning to simplify this process with CI automation, but I think it is still worth understanding how to do it locally. On the next few slides, I'll cover a few suggestions to make the OpenAPI for your plugins even better. First, when you're constructing the regex for your path pattern, make sure to take advantage of the Vault regex helpers. Custom regexes may not work very well with the OpenAPI. Next, if you have endpoint specifically for list operations, it should end with a slash. This is a convention we've been following with Vault and OpenAPI spec. For better documentation, be sure to populate the summary and description fields at the path and operation levels. The next three I'll cover in a bit more detail, but to summarize, framework.fields will map to a request object in OpenAPI, response.fields will map to a response object, and display attributes operation fields will map to operation ID, which in turn translates into a method name in the generated code. So framework.fields that you can see here will be used to generate the request body object in OpenAPI. The one exception to that are path parameters. They will be present in framework.fields but excluded from the generated request body. Response fields map is something we've introduced quite recently, and it will be mapped to the response object corresponding to this operation. You only need to define the successful 200 level response schema here. As you've seen in the demo, we have a few test helpers that allow validating responses against response schema, and you're highly encouraged to use them. Finally, be sure to populate the display attributes with the operation prefix, verb, and suffix. These will be translated into operation IDs by concatenating the three parts into one hyphenated string. And the operation IDs will map into the method names in the generated code. If any of the prefix, verb, or suffix are omitted, the OpenAPI code will attempt to fill these with reasonable defaults, like the verb would default to the operation name. But if you want to control the names of the generated methods, be sure to populate all three prefix, verb, and suffix. So one of the best uses of OpenAPI spec is generating client libraries. And we now have two new libraries currently in beta, Vault Client Go and Vault Client.net. Let's take a look at Vault Client Go first. Once it is fully released, it will be a successor to the existing Go library that we currently have under Vault API directory in the main repo. Alright, let's take a look inside. Here we have a number of handlebar templates that are specific to this repo and I used to generate the code. And this is what the generated code looks like. Let's find our kvv2 read configuration function. This one is still referring to the previous version of OpenAPI.json, but we can easily regenerate the code. First, I'm going to copy the OpenAPI.json file we just generated into Vault Client Go's directory to override the existing one. And then I will simply run make regen to regenerate all the files. And now, as you can see, both the request name and the response name have been modified. And max versions demo as well. Great. Now let's see how to use this library. Here I have an empty directory. I'm going to navigate to GitHub HashiCorp Vault Client Go. And copy over the getting started example. Next, let's run gomod init and gomod tidy. Let's also start a dev vault server in the background. And just like that, we're writing and reading our first secret. So there are many awesome things that you can do with this library, but I'll just demo a couple more. First, when you initialize the client, you can pass in various options using with-x pattern. For example, I can configure the client to pull in environment variables using vault.withenvironment call. And now my client respects vault_adder environment variable. Similarly, each request can be decorated with various modifiers. For example, here I'm adding a request callback to print out the request before it is sent. Most of these request modifiers also have global client level analogs as well. For example, client.set request callbacks here. And now the request is printed out as expected. This is it from me today. Thank you for listening. And now on to Anna to discuss another OpenAPI-based library that we've developed, vaultclient.net.
Hi, my name is Annalise Diroff. I'm an engineer on the Vault DevX team. Today I'm going to be showing off the .NET Client library that's based off the OpenAPI spec for Vault. I'm going to create an application from scratch. I'm going to show you how to add the .NET library to that application, and then I will read and write a secret from Vault using that library. I'm also going to show off some of the functionality that we built on top of the base generated library. And then I'll also show some of the workflow and how we actually generate the library from an OpenAPI spec. So first things first, I'm just going to create a new application. .NET has a scaffolding tool that will just create all the files that we need from scratch. So I just created a console application. you'll just see it does a basic hello world. And I'm going to hop over to NuGet. So this is where our HashiCorp Vault package lives. It kind of shows you how you can include it in your project. I find this using the .NET CLI tool to be pretty straightforward. So I'm going to go ahead and copy that and use the latest version. So I'm going to paste this into our project, and it should add everything we need. So if we go to our CS proj file, we'll see that it's added HashiCorp Vault as a package reference. Perfect. Okay, so now I'm going to hop over to our Vault Client repo. So this is the Vault Client.NET repo. It is currently public in beta right now. And the README has a lot of examples how to install the library and how to use it. It has getting started and some of the custom functionality that we talked about as well. So if we scroll down, we'll see that we have some examples. There's a very basic getting started example. So in the background right now, I have a Vault Dev server running with my token set as the root token ID. So this should work. This example should work for us. So I'm going to go ahead and copy this, and I'm going to paste it in our program CS. So I'm going to overwrite all this here. Okay, so now we can go ahead and go over the code. So what you do with this client library is you create a basic Vault configuration. It only requires an address. So right now we're just pointing it to the local Vault instance I have running. And then we can use that configuration to create client. I am then setting the token, which is the root token that I gave to Vault. Typically, you'd want to use an authentication method like AppRoll, but in this case, this will work for demonstration purposes. And then we're going to go ahead and write to the KV-v2 backend. We're just going to write a basic password, and we're going to write it to the path, my path. And then we just read the secret back. So we're just going to read it from my path, and we're going to print out the data. So if we go ahead and run this, we're going to go see this should work without any intervention. Bob's your uncle. We got our password back, and it works just fine. Okay, so now that we've created a basic application, I wanted to run through some of the things that the library can do and some of the things that we care about. So for example, if we look at the Vault client, some of the things that we care about, we have auth, so that this object is going to contain all of our auth backends, so things like AppRoll login, if we wanted to use that. You'll also notice that each call has both a synchronous and an asynchronous endpoint, so we support both. There's also identity that has all the identity related calls. And then we also have things like secrets. So this is going to be your KVs. There's also Cubbyhole, and all of the secrets engines that are built into Vault are under there. Finally, the other main object that we care about is system. So this is going to have things like sysmounts and monitor and wrap and unwrap. So those are the main high-level objects. I'm going to hop back over to our README to show off a little bit of the custom functionality we have. So there is currently, with configuring a client, you can do a few custom configurations, such as set a custom timeout. You can also set a custom HTTP client handler, which is a .NET thing that is effectively like a request callback. You can also, we allow for setting certain types of headers. So you noticed we used set token to set the header token that would go with each Vault request. We also have the ability to set and clear namespaces. And then we also allow you to pass in custom headers as well. We kind of saw a little bit about Vault authentication, but again, all the auth endpoints live under this auth object. So if you wanted to do AppRoll login, you would call the login function, create the login request object, give your role ID, give your secret ID, and then that should do it. Another thing that we allow for is overriding the default mount path. So if you're not using the default mount path, all endpoints have an option to override that and provide your custom mount path that you're using. And we've already seen reading a KV secret. We also allow for you to wrap and unwrap responses. And Another really important one is performing generic operations. So if you have a plugin that is not native to Vault, it's not built into Vault, it will not be built into the library. So you can use the read and write generic operations to interact with those backends, with those custom backends. Okay, so now that we were able to successfully read and write a secret to Vault using our application and our .NET Client library, we're going to hop over to a new instance of VS Code that I have the Vault Client.NET library open in. I kind of wanted to go over some of the code in here and the way things are structured to make it a little bit easier to digest. So a couple things, we have the OpenAPI JSON in the root of the repository. This allows us to generate the library from scratch. It likely will not be living in here forever as a source of truth, but for now, this is a place you can find it. So you'll see path names and all the parameters, etc. And then the templates that we actually use to generate the code are under this generate folder. If you pop open the templates, you'll see there are a bunch of handlebar templates, and they're all in this handlebar format. They basically just allows us to, inject certain things into the code. So you'll notice the structure of the code looks similar to C# with some things redacted that are injected with either the config or with the OpenAPI spec. And then we also have the source folders. So this is generally the auto generation. So most of these are auto generated, and you do not want to be messing with these because they'll just get overwritten. So we have our main Vault client. So this is, you'll notice it has the auth, identity, secrets, and system. So those top level things. And it's got, this is just basically how you would normally initialize it. And then inside you have the API. So these are all of the implementations and the interfaces for the different endpoints. So there's all the AWS things, all the Azure app roll auth. We also have our identity endpoints and our secrets and our system as well. And then if you pop open the client, this is just basic other kind of ancillary things like the configuration, the client, exceptions, things like that. And then in the models, we have all of the request and response models. So these are objects that you would pass to an endpoint that would contain all the request information, or the objects that you would receive back, like the response models. And we also have a makefile. So this hopefully makes things a little bit easier, but I'm not going to run these regens because they take a little bit of time. There's a lot of files to generate. But the regen will delete all the generated files. It will generate everything and format and clean. And the regen bin will build it and create a binary. And if you want to develop locally, you can regen and use the bin and copy and paste the binary into your directory to test or play around with. I think that about covers it. So thank you so much, and please give it a try and let us know what you think. Thanks.
Thank you so much, Anton and Anna, for going over the various client libraries and, of course, how to make your own OpenAPI spec with Vault. Super neat to see the manual workflow. Also excited to see that included into the CLI directly. And also it was awesome to see the other options interact with Vault as a client, both through Go and through .NET. But next up, maybe but wasn't the right connector there. But next up, we're going to hear about what's titled Maestro. Nomad is actually an orchestrator from Daniel Bennett. We're going to learn about creating custom task drivers in Nomad with music, whimsy, and MIDI. Now, most of y'all are probably accustomed to running tasks like containers or Java jar files with Nomad, but we're going to see what else it can be run with. So whenever you're ready, Daniel, take it away.
Hello, builders. Thank you for coming to my talk. I'm Daniel Bennett, Nomad engineer at HashiCorp. I'm here to tell you about my MIDI task driver for Nomad that turns Nomad into an actual orchestrator that plays some music software like, in my case, Ableton Live. I'm going to try not to apologize for not being a professional presenter, so sorry in advance if I do apologize for that. At the end of this, there will be a demo, so if you have headphones nearby, go ahead and grab those so you can hear my sick beats. All right. What's this all about? Like you, I assume, I am here to learn. And I love to learn by making silly projects. I've made a deep, dark secrets engine for Vault, distributed Conway's Game of Life on Nomad, where each cell was a Nomad job before I joined the team. And shortly after I joined the team earlier this year, we had a hack week, and this is what I did for that. So what this is all about today is we'll talk about how music is made briefly and how I crammed Nomad into that picture. Talk about task drivers, how they usually work, like high level at least, how mine works differently and worse, but in a convenient way for a hack week and for music coordination. I'll show you my MIDI job specification, how I templated it with Pack. I'll do a quick little demo and walk you through the Ableton setup on the music software side. We'll look at some code, which hopefully y'all are excited for. I'll play a song-length demo right towards the end, and then I'll encourage you to go forth and make your own weird or useful or both task drivers for Nomad. So first up, how is music made, and can Nomad help me with that? Nomad can't really help you make better music, but it's not supposed to. I don't know why you would expect Nomad to be able to do that, so it's kind of on you, really. How music is usually made is you have a DAW, a digital audio workstation like Ableton or Pro Tools or FL Studio or Logic. There's a whole bunch of them. And you push buttons in this piece of software, and you play instruments into it or push more buttons until you're happy with it and music comes out the other side. But in my many years now of dabbling with this here and there, I talked to a lot of musicians about songwriting and music making, and everyone unanimously agrees that it is too easy to make music this way. Making music is too easy. So let's engineer our way out of this problem. We'll keep Ableton in the picture here, of course, but we're only going to use it to produce a MIDI file. It's just a handy editor to be able to produce a MIDI file for us. And this is a file that contains which notes should be pressed at what time and how hard and for how long, stuff like that. We'll do that for each instrument. And then we'll feed that into a Nomad job specification, which is templated by Nomad Pack, which is pretty nice for demo purposes, and just in general. So then that MIDI file, still just a file name, will get fed over to Nomad as a job. Nomad will go, hey, I need a driver for that, and it will use my MIDI driver. MIDI driver will slurp up that MIDI file, process it, and then send the actual MIDI instructions over a MIDI port that's running on my Mac here. Ableton will listen on that port and then produce the music. This is what we really like to see as engineers. Really nice, complicated flow diagrams. It's just the best. Cool. So how do task drivers work? And how does mine not work as good? This is how things are usually set up. You've got a Nomad client agent running on a host machine. It receives some work to do, and if it doesn't have the driver plugin built into it, like Docker is in there, exec is in there, and some others, then it will launch a driver plugin binary, which gets a process started, and then it will talk to that process over gRPC, and send it some pretty sensible instructions about, Nomad-y things to start and stop tasks and so on. And the driver process speaks over, I put API in quotes here because API usually makes you think of like a REST API, but very much not necessarily so here, although it can be. It might just be a command on the operating system. Hey, please run this command for me. It could be speaking over a Unix socket, maybe to Podman or Docker to run a Docker container. It could be asking QEMU to spin up a VM for us. And then that thing does the heavy lifting, which produces an actual workload over here on the other side, which is the thing that we really care about. This is really nice for at least a couple of reasons. One is that this can have all the real business logic that it's concerned with. It can be rather complicated how it manages all this stuff. But then on the driver side, you can have a pretty thin, almost like a client to a server kind of relationship here. So the driver code may have only enough logic in it, or a little more logic than to read configuration from your job specification and sort of forward that along in a meaningful way to whatever it wants to talk to. Another reason this is nice is that if this stuff goes away, which happens, maybe it just got restarted for some reason, this other stuff can continue running. And you might even imagine that like this runs somewhere totally else on a different machine even, although that is really rare, it could happen. And also whenever this comes back up, it loads some state off a disk to see what it thinks the state of the world should be. And it kind of compares that with the actual state of the world to load back up into memory, where it left off before it shut down. So it can sort of take control back of whatever's running over here. So that later it can stop it or issue commands to it or whatever Nomad might want to do with running task. That's all great and wonderful and nice and stable, and that's why everybody does it that way. But I didn't do it that way. I cut out all the sort of servery side, daemon-y kind of persistent thing outside of Nomad, and I'm just going to run everything in a driver process. So in my case, my task, instead of being run a Docker container or execute a command, my task will be a go routine within the driver process. That's really convenient for me because with music, you need to coordinate multiple parts of the music together in very precise timing. And Nomad doesn't do that on its own. If you have separate tasks, then Nomad just like tries to get them up and running, and it doesn't really pay any heed to your sensitive ear to try to make something that sounds like music. And if it gets off at all, then it turns quickly into noise. So we need to be really careful about our timing. So I just put it all into Go routines in this driver process so that I can have my nice strict timing. You might see like a problem with this picture, which is that if that stuff goes away, well, the music stops playing, right? Because Ableton is just sitting here listening on this port and nothing's going down it. So if my driver process crashes, our Nomad client restarts, which tends to bring the driver process with it until it launches it back up after a restart. Then Ableton will just sit there quietly. But that's totally fine. I'm sure nothing will go wrong, and it'll just work fine all the time. And it's Hack Week. If I was going to do this right and like productionize my MIDI driver for some reason, then I would make a little daemon that ran out here that, again, the driver would just be like a thin client for. And it would be mainly responsible for integrating with Nomad, and then have a separate thing, like the previous picture, to keep things up and running. But again, it's Hack Week, so screw it, just shove it all into one process. Cool. Well, I'll show you kind of what I'm aiming at, and then we'll walk through how we get there. So our target is to have a job specification that looks a little something like this. And it has, job name, group name, task name. This is a mallet. It'll go clunk, kind of a sound. So that's one part. This all represents one instrument playing. I tell it my driver, which is not as catchy as Maestro, but gets the job done. The song here is just a string that is used as it's basically like a key and a map of clocks. We're only going to have this one song, but this is what allows my driver to synchronize many of these separate jobs. So you give it the song name, and as long as they all have the same song name, then it will line them up on a clock that I get going based on this. Feed it the MIDI file so that it knows what to read to then process and send over the MIDI port. MIDI port here is the name of the virtual MIDI port, which is in OSX, it's got sort of built in this way to create these virtual MIDI ports, and I've got one for each instrument. So that's great. And then bars is how long the MIDI file is. You want to have different length instrument parts, otherwise it will sound quite bland. But I didn't teach it to process this file to try to figure out how long it is. Again, hack week. So I just tell it, hey, this is 1 bar, or it's 2 bars, or it's 4 bars. So only play it as often as makes sense for that. So I'm sitting here looking at this, and I see mallet, 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 and it's just begging to be templated, right? And this is hack week. I haven't really played around with Nomad Pack all that much, at least not making my own. So this was a great opportunity for me to play with that and learn a little something more as a nice little side quest on my main MIDI project. So this is kind of what that looks like. This is the template. I exclude some other files that Nomad Pack needs just for brevity here, but basically I can feed in this one part name now, and it gets fed in and templated as you might imagine templates do. And as a result, I can run my single instrument much more simply by feeding it just this one nice, unique word, which I can even, alias down to run mallet. So here's kind of how that works. I'm going to hit run mallet. If I've got my audio set up, you should start hearing it now. And over here in Ableton, we've got a mallet, 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 and this is the MIDI information coming through, and this is what Ableton's doing with it. I'll go ahead and stop that. And that'll quiet down. So while we're here, I'll show you kind of how Ableton is set up. I named everything consistently, so this is just the name of the track. This is the port itself, so this maps over to the MIDI port on the machine, which I feed through the job spec, which talks to the machine port on the machine, which gets listened to by Ableton here. And named everything consistently kind of across the board, strings, strings, and so on, just so I can keep things straight in my head. Each one of these is like the actual track. So for strings here, this is the MIDI data. I did sort of my composition here, just because I'm sort of comfortable in here. And then I can export the MIDI clip, which produces the MIDI file. For any of you MIDI folks who are wondering why all these dang ports and not just separate channels on a single port, for one thing, I want to avoid the word channel because that's a Go thing too. I'm kidding. But really, as far as I can tell in the documentation for Ableton, exporting a MIDI clip from Ableton just has this limitation. You can't export a MIDI clip into more than one channel. Each export just has one channel. I could have produced these files differently to avoid that, but hey, it's hack week, screw it. So I've written all my parts, and I've spruced up their sounds and made them sound all neat and interesting. And I exported my MIDI data out to files, so I can just delete these now. And later on, don't catch me cheating, this will not be running. Everything will be driven by Nomad, by my driver plugin. So I think we hop back over here, and we'll look at a little bit of code. Finally, we got here. So this is the interface that we need to implement. It's in the Nomad repo. You can go and have a gander there. There's a bunch of things that you need to implement that are important for Nomad to know. We'll focus mainly on these, start, lesser extent, wait, stop, and destroy. We'll kind of walk through those because that's what mostly you care about, I think, whenever you're writing a driver. It's like, I want to do the thing, and then when it's done, I want to make sure it, gets cleaned up or whatever. So this is the interface that we'll be implementing. Here's my repo of my implementation of it, hacked together in a couple of days. Not apologizing, that's right. Here's the driver template that I use. So I just cloned this thing. Thank you, teammates, for leaving this lying around for me to just like steal and modify to suit my own purposes. It's got to-do comments throughout it, which are quite helpful to keep you sort of on track and to let you know what all sorts of things you might want to change to get your driver plugin set up to do what you want it to do. Thanks to the maintainers of this Go MIDI library, it speaks MIDI, so I don't have to. Super handy to have. There's a bunch of drivers too. In particular, mine, I used port MIDI on my MacBook here, but there's a few different ways to drive that MIDI data. And now we'll go through an IDE and walk through the actual code. So I'm going to stumble a bit through here probably, but just bear with me. This is main. This is the entry point for the driver, and that's where Nomad will go through. And it expects this to have happened to set up all the gRPC listening and so on. In my case, I added a little bit extra up here so that I could run the plugin outside of Nomad to get it functioning how I kind of wanted it to, without wondering whether I was screwing up on the Nomad side, or even just to run it over and over again really quickly without needing to have Nomad involved the whole time. But mostly what we want is plugin serve. And that expects a particular interface. It expects a plugin factory, which we've got right down here, as you might notice. Interface, this is always a bit of a smell, right? The reason that it's an interface is that you might have, I'll hop over here into serve, and serve takes that a function with that interface. Serve here can take more than one kind of plugin. It can either do a device plugin like NVIDIA or USB. These are devices, or it can do drivers. These are much more common. It's what we'll be making today. It's Docker driver and so on. And exec and such are all driver plugins, and that's what we will be making. So we'll hop back out up to here and go to our factory and to my little new plugin, which, hey, look at that. I did brand that one. How about that? Cool. So new plugin, I make sure for my own sake that I actually am implementing driver plugin here. Then we'll hop down to start task. There's a whole bunch going on that, again, I'm going to kind of glaze over. Apologies if this is what you were really here for, was to learn about fingerprinting and such. It's really interesting stuff. Look into it, but I'm not going to talk about that today. So, start task. The client has asked the server, hey, do you have any work for me to do? The server goes, hey, it looks like you can do this job. You've got what I need from the fingerprinting that we talked about. So here, do this job. Then the client passes this task config thing via gRPC again over to my driver plugin. It's got a bunch of stuff on it that you might find to be relevant and interesting for your driver authoring needs. For example, I could have used an allocation ID if I wanted to put all of my different instruments or tracks or parts in as separate tasks, but still all within one group. Then I could have excluded that song key and had like each group gets its own clock. But that doesn't look as nice on a demo. It's cool to have separate jobs that have, nice clean names. So mainly for demo reasons, I just kept the song in there instead. But you might imagine that you can do interesting things with these in your drivers. It comes with this convenient little thing to help unpack the task config, which is going to look familiar here. So we've got our song MIDI file and port name. That's pretty cool. We're starting to connect up with our end goal. So that's nice. We get a task handle, and we'll kind of hop in there and you can see what it is for. It's for state between the driver and the client. So for example, I can tell it, hey, Nomad client, I'm running now. So we're good here, or I've died, or so on. It also can be used during recovery. There's some state that you can add stuff in here to persist across driver restarts. But we're not going to bother with any of that. We're just going to let it all crash and burn and pick up whenever it starts back up. That's fine. We have a stateless app. Everybody loves stateless apps, right? That's great. Cool. So we got one of those. This thing is Nomad-y stuff again. We'll get a context, a cancelable context. And we'll hang on to this stopper for later so that we can issue our stop command when we get there so we can cancel the context when we get down to stopping the task, which should stop our player and so on. But we're getting a little ahead of ourselves. We'll get a clock, again, based on that song name. So we get a clock, and each task that has the song will get the same clock. I'm doing the global state thing, because again, this is hackathon. Whatever, man, it's all in one process. Let's go. I'll make a new player that gets the full config, and we'll bump into that later. The player actually plays the MIDI file out to the port. And we'll subscribe the player to the clock so that when the clock ticks, it can let the player know, hey, it's time to play your tune if you feel like it. And then we've got some more Nomad driver state stuff, sort of statefully Nomad-y integration stuff. Again, apologies if this is the meat of what you wanted to be here for. But hey, doesn't that look just tantalizing? You should just go and find out what that does yourself, get your hands in it, Cool. So now we get some work actually going. I get my clock started ticking. You can always be sure whenever I have a long comment like this that I had a nasty bug that was really challenging for me to figure out. I left myself a note. So that's kind of fun. We get the clock ticking, the player playing, and then we start this other thing, which again is for Nomad reasons, basically. We'll set some state on our task handle so that we can let Nomad know what the result of this was, like if it crashed or anything. Cool. So we'll hop into our clock ticking. Remember, we've got one global clock for everything that is in the same song. So we only want that to be ticking once. So this just guards against it ticking more than one time. We got a timeout in case we get a rogue player. We got our good old infinite loop golang select, for select thing with some exit conditions as you gotta have. And then we have our time ticker that ticks for us. We set it up before during new clock. On each tick, we get a lock of our subs just in case, we collide here, we want to be careful. So for each player, we send a bit of nothing info, kinda, down it, real lightweight empty struct, just to say, hey, player, time to tick. And if that times out, then we don't want to, stop the whole world and the whole song. So we make sure that we've got a timeout set there too, in case the player isn't actually listening on this channel for whatever reason. I may have encountered time dragons at some point during this process, so you get nice debug messages like trying to send to. But anywho, we'll head back out to our driver here and look at our player. which actually gets our job done. So we pull the port file and bars out of our config. That's all fine and dandy. We ask MIDI, hey, could you please find that port for me? And if you fail, like, let's make some noise about that. Go ahead and wrap up. This is a little construction to only finish the go routine in here after the music is done playing. We don't want to stop partway through the music playing. So this just makes sure that that happens. We set bar to 1, and we'll talk about that in a sec. We've got another infinite for select with our exit conditions. Escape hatch that, you have to imagine I hit a bug there and found some reason to have that. This is the clock has told us to tick. So great. I mentioned bars before. The clock ticks once per bar. That's its sort of granularity. So if we have a track that is more than 1 bar, we don't want to play it on every bar, or it would kind of stack up, right, and play on top of itself. So we just do a little extra work here to only play whenever it's make sure we don't overlap. We only play on the bar that we need to. Do some more logging. We use our MIDI library again to chew on our file and then to play it to our output port. And now we should have music playing. So looking pretty good. Next up is recovery. JK, not doing that. There is no recovery here. Wait task is, Nomad has cause. It's alloc runner, I believe. Don't quote me on that. At any rate, sometimes the Nomad knows that we need to wait on things to complete, so it does that there. I know that whenever I want to stop my task, I want the music to stop playing, as you might imagine. So I get a cancel context here, or a timeout, excuse me. Nomad gives us a timeout, and this can go through the job specification, I think. So we want to respect, right, the timeout. So if it tells us to stop, but only try for so long, we want to respect that. So we give it a context to only wait for that long. But we unsubscribe the player to the clock so that the clock doesn't try to continue sending ticks down it to its channel. We stop the context that we set up and run task, which should cascade down, and player's wait here should catch that and bail out. Then we also want to clean up after ourselves. So in another task, your task might set up, say, like network rules or something. But here I have a piece of shared, state that sort of sits around afterwards. And that's my clock. So I need to make sure that I clean up my clock from memory. Really doing some real heavy lifting, deleting my 1 clock from memory, from global state. All right, well, that was a walk. Let's hop over here, and I will get myself out of the way, and we'll play the demo. Hope you enjoy. Thank you, everyone, for tuning in. I hope you enjoyed the show. I hope you understand Nomad task drivers a little better, and I hope you feel inspired to make your own. It's a lot of fun. It really can be anything. Okay, bye, builders. Bye. Bye now. Bye. Bye.
Thank you so much, Daniel. That was a great exercise in both, well, obviously creativity, and kind of fits the spirit of what HashiTalks build was put together for, right? Building really neat things. Not only did we get to see a workflow and something put together that you're not really going to see typically worked with, but we also got to learn how to do things in general. And it kind of points out the big differentiator for Nomad is, well, what can you run on it? What can you orchestrate with it? Well, if that doesn't prove pretty much anything, then I don't know what will. However, across the ocean, in the other world of orchestrators, there is the beast known as Kubernetes. And what would a tech talk circle, whatever we're calling this, be without some more Kubernetes? So next up, we have a talk with Scott McAllister, who's going to talk to us about building Ingress in Kubernetes and Consul with ngrok. And this is going to talk about creating a custom secure Ingress controller for Kubernetes. And for those who were here for the Nomad stuff, or may not be as familiar with Kubernetes, this is going to be the thing that lets you get into all those services that you've got for Kubernetes. So Scott, when you are ready, enlighten us.
Hey there, HashiTalks build. I'm Scott McAllister, developer advocate at ngrok. Today, I want to take you through our journey of building Ingress into Kubernetes with ngrok. This is not meant to be a sales pitch, but I will be talking about our company, its features, its products, because you need to know the context around why we made the decisions that we did. Because we're going to be talking about the trade-offs that we went through in order to provide the features that we needed for ourselves, but also for our customers. Now, your needs, they might be different, but this is our story, and hopefully you can learn from some of the experiences that we had. To give you some background and make sure that we're all on the same page, I'm going to talk a little bit about ngrok, describe what it is, and give you a sense for what we provide and why we made the choices we did. Then I'm going to talk about containers and Kubernetes to cover some of the terminology and concepts. That way we're all on the same page. And finally, I'll bring all those together and talk about how we brought everything into one nice solution. So the story of the day is trade-offs. You'll be hearing me talk a lot about trade-offs because in every project, we have decisions that we make. We have decisions that are based on our needs, whether they're for us or they're for our users. But the philosophy we took was, if it works for us, then why not for our users as well? So think back to a time where you created a new project. It was awesome. You were so excited about it. You had everything in it that you thought could possibly be great. And you knew that the moment a user got their hands on it, they would also love it as well. No one could tell you that it was ugly. No one could tell you that even if it was green and had little green arms sticking out of it, that it was a bad thing, because you knew it was awesome. It just had to get into a user's hands. But that was the thing, that was the issue. It needed to get into a user's hands. And to get from your machine onto a user's machine, or at least onto their device for them to use it, there's a gap. You have to set up some network connectivity settings to get your application online so that people can use your application, so that you can have customers, and so that you can actually continue building your application. To do that, you might have to think about, well, let's think about setting up some NAT, and maybe configuring DNS or messing with certificates. And that's just for this one service. What if I add more services, or I take my application from my laptop and take it into my office network and start figuring out, okay, well, now I have settings I need to think about getting through a firewall or a VPN or all these other configurations that you need to be an expert on in order to get your application online. Not only online and accessible, but also online, accessible, and secure. so that you can have secure traffic with your application? Well, that's where ngrok comes in. Ngrok is a service that allows you to not have to worry about that connectivity. No matter where your service is running, your network settings are the same. You point ngrok at your service, and ngrok does the rest. Essentially, you're connecting to ngrok, and ngrok will connect your application to the world. And it traditionally does that as an agent that runs in your command line. ngrok does that magic where it takes the port you specify on your machine and makes it accessible to a URL that either you specify or the ngrok returns for you. You give it a command like this. It says ngrok, say HTTP, which is the protocol you want, and then on port 80. So we said port 80 here. We specified a domain, and we get a response that says, here is traffic that's going to be going to this URL. We'll route it to that port on your machine. Now, the reasoning behind all of this is an idea that's shared by our founder, Alan Shreve. If you think about all of the other parts of our development lifecycle, many of them have been abstracted out. Very few of us are programming in low-level languages that are close to bare metal. We're working on those high-level programming languages. And then even then, many of our front-end engineers are saying, well, yeah, JavaScript's awesome, but why not use these frameworks as well? And many JavaScript engineers are using frameworks like Angular, React, or Vue. Again, abstracting out some of the tedious parts of using whatever the lower language they're abstracting from. If you're working with an API, say, very rarely are you making HTTP calls and parsing JSON. You're connecting to an SDK that says, hey, I'm already working in Java, so let's keep working with Java objects and make sure that we can just have this connectivity between me and another system, rather than saying, let's make this HTTP call, then let's parse this JSON into Java objects. An SDK should be written and probably abstracting out that API traffic for you. Same concept with ngrok and our network connectivity. You have all these important settings that need to be configured so that your application is online in a secure fashion. Let us handle all of that, and you focus on getting your application and making it work. We'll make it environment independent, so that way you can have that same connectivity from your laptop or in a data center or in a cloud provider. All those things are available through ngrok. Okay, that's enough of my sales pitch. Now, going back to your application, our application is growing. People love it. You were right. The market loves it. People love it, and they're using it, and they're asking for more features. So you need to add more services. So to do that, you probably need to start thinking about, okay, if my services, if I'm gonna have more of these, I need to start thinking about how to build this in a more constructive sort of way. So why don't we do that with something called containers? And when we do that, all of our application code and the dependencies are run, they're stored inside of the container. Containers are their own portable computing environment. They contain everything you need to run the service. Containers run on an abstracted layer above the host operating system, which makes the container extremely portable. They just run in the container runtime, which is something like Docker or Containerd. Now, most applications will have multiple containers running, especially as the application adds features, other services, or even scales. And that's where Kubernetes comes in handy. Kubernetes is an open source container orchestration platform that automates application deployment, management, scaling. It's also been described as a cluster management system, something that I had to learn as I was learning about Kubernetes, where it's taking our services and clustering them together to help things be a lot more efficient and easier to manage. As we talk about Kubernetes, we're going to cover a few concepts, enough terminology to explain what we're doing and how it relates to the flow of information. There is a lot to Kubernetes. It's a massive environment with many other nerd knobs and settings that you can configure while managing your Kubernetes clusters. So we're only going to cover what we need to know today to talk about Ingress and talk about Ingress with Consul. For starters, in Kubernetes, containers live inside of an object called a pod. For this diagram, we're only going to keep our pods on a one-to-one relationship with containers. So we're going to have one container running inside of each pod. So think of a pod as a sandbox for hosting containers. And in the spirit of abstraction, we're going to abstract out the diagram of our containers and just look at our pods now. It's almost like we're pulling the lens back from looking at containers, and now we're going to be looking at Kubernetes. And in Kubernetes, the smallest object, or the atomic object, I believe is what they call pods. Okay. And so pods, as we are building our application, we're going to be adding more pods. We're going to be adding more features. We're going to be scaling things. So we're going to have multiple pods in our application that are going to need to talk to each other. And with those pods, that communication happens through an object called a service. That's right, just a generic name like service. It kind of reminds me of that old programming joke, the 3 hardest things in programming: naming things and off by 1 errors. Yeah, you're welcome. Essentially, a service provides that ability for pods to communicate with one another. Think of pods as being on their own virtual private network where they can only talk to each other and no traffic can really get at them from outside. They're just the ones talking to one another on the inside of their cluster. This network traffic between pods is commonly referred to as east-west traffic. To allow outside traffic into the cluster, you need to configure something called Ingress, and this is known as the north-south traffic. An Ingress object uses one or more Ingress controllers to set the rules of that communication. And an Ingress controller can be one of several things. It can be load balancing the traffic that's coming at your cluster. It could be providing name-based virtual hosting. It could be providing authentication to that for accessing that cluster. Lots of controllers can make up Ingress and can provide different functionality. You can have one controller or many. So in order for Ingress to work, the cluster must have an Ingress controller running. I should say, in order for traffic to get to that cluster and for Ingress to work, it needs to have an Ingress controller configured and running. It's not going to be done automatically. There's a lot of other situations in Kubernetes where controllers are automatic and they spin up on their own as the application spins up. Ingress is not that way. Ingress is something that you have to specify through using at least one Ingress controller. So a common setup is to have an Ingress controller providing a proxy to the cluster. So we have an Nginx Ingress controller, and then another Ingress controller that's providing load balancing. So in this case, because it's orange on our screen here, we can assume that this load balancer is probably for Amazon, which illustrates the point that the load balancer is usually tied to the environment that you're running in. And so if I'm running this in Amazon, that's great. But if I want to take my application and for some other reason move it to another cloud provider, or maybe pull it in-house and into our own data center, our own machines, we'll have to configure another load balancer. We'll have to figure another Ingress controller to figure out how are we going to divvy up that traffic so we can balance the load coming in. But let's step back for a second and talk about ngrok and our journey. So ngrok started as a project by Alan Shreve when he was an engineer at Twilio. He needed a way to provide Ingress to code running on his laptop. He was working with webhooks, and he needed a place for those webhooks to go. As webhooks behave, they need an address that's publicly accessible to the internet to operate. They take their information, they send it to that address, and then that address parses whatever that webhook is sending. Well, Alan needed to provide Ingress to his local machine and thought, well, I could go through the steps of setting this up on my machine, or I could make it something that I could just spin up a tool that does that for me. And then maybe it's not tied to this specific laptop, because what if I go to another laptop? I could have my own little tool that does this and provides that Ingress. So he builds this thing and he gets excited about it, shares it with his team. They get excited about it. He shares it with the community. They get excited about it. And then people are actually like so excited, they want to pay him money for it. And he's thinking, wait, I could build a company around this. And as he's building that idea and thinking, all right, this is now going from hobby project to possibly a product that I could sell and have, build an organization around, I could have a software startup. And as many other software startups, he ran into that age-old architectural philosophical decision. The monolith or the microservice? Which way should I go? On the one hand, you have the monolith. which has a lot less infrastructure complexity, but it is also everything all in one place. It's super fast, and as a startup, speed is the name of the game. Getting features out, released, published. That's the part, that's the thing about startup that you need to happen. That's most important. With microservices, yeah, your code's more organized. You have your concerns separated, true. And things take a lot more effort to launch. You need to put a lot more effort into your infrastructure. So he had a conundrum. He knew he eventually needed to go to microservices at some point, because as your organization grows, that makes a lot of sense to have a services-oriented architecture. So rather than making a solid decision one way or the other, Alan kind of went up the middle and came up with a hybrid idea. He called it the Neo monolith, or he also used the term Lego monolith, which I latched onto because I can visualize Legos a lot easier than a Neo. Who knows what that even is? So with the Lego monolith, you can imagine building blocks inside of a larger thing. You have that big purple box there in the middle. That looks a lot like a monolith. However, each of the services in that monolith are named the same. No matter how many monoliths, no matter how many boxes, VM images he has running of his application, they're all the same. The services have the same names, the same ports. And so there's no need for service discovery. There's no need for scheduling. There's no need for any orchestration complexity. He's able to easily scale because he can just replicate the boxes. And then yet also it's organized internally inside of each of those boxes in a way that he has a clear path to migrate to microservices when the time comes. So he took an idea that when he needed it, he could use service-oriented architecture, but he didn't have to have it straight up. It turned out nice. So as he built out the organization, as they started making decisions, and I say they because these are people that were at ngrok way before me. And so when they made these decisions to go to a service-oriented architecture, they started saying, okay, let's start adopting containers. We're going to start adopting Kubernetes. But in Kubernetes, we need to configure Ingress. Well, we have this product that provides great Ingress to developer machines. Why not also provide Ingress to production environments? Why not dog food what we have to see if other people could use the same benefit? They could use ngrok as a production tool and benefit from the ease of use that it provides. And they weren't the only ones who thought this. Actually, this diagram was created by users of ngrok and Kubernetes, not just, they weren't actually internal at ngrok. So we initially adopted a strategy that was a lot like this, where we ran ngrok, the agent, we took a binary of the agent and ran it as its own service. Remember, capital S service in Kubernetes. And it did something like this, where it essentially exposed an Nginx service, which in turn would expose everything to the internet. I mean, it worked, but it was a little weird, right? Not quite a sidecar, although others have done that as well, but definitely not the preferred way of doing things in Kubernetes. In our case, we still needed to write custom Go code to shoehorn the agent to work the way we needed it to. We even needed to change our own product. And users still needed to configure, or at least understand how to configure ngrok independent of Kubernetes, but then also know how they can make it work with the Kubernetes setup that they had going on. It wasn't a expected way of doing things where you have YAML manifest files, but a lot more work. Even internally, we went as far as creating our own custom instance of ngrok, and it started branching from the one that the world was using and the one that we're using. And suddenly you're not dogfooding anymore if your product is different than the one that your customers are using. So it wasn't an ideal situation. We had a couple of decisions we needed to make going forward, essentially. We had to make some architectural decisions on our relationship with Kubernetes and how we would want to integrate with the Kubernetes ecosystem. But then also we needed to make some decisions inside of our product as well. So looking at the Kubernetes architecture and how we would connect with Kubernetes, we wanted to have an idiomatic API. which in other words meant we wanted to be able to behave as expected as the other Kubernetes controllers and objects. We also wanted to seamlessly, essentially hand in hand, right? We wanted to seamlessly integrate with Kubernetes and the Kubernetes ecosystem so that we could work well with clusters, but also work well with things like Consul, so that Consul provides great service mesh. Why not provide Ingress into things like Consul so that folks can easily connect their service mesh to the world? So those are some of the things we had to take into consideration for our connection with Kubernetes, but then we also had to make some product decisions. We needed to make some things available in our product so that our users had what they wanted while using our product. We needed to be able to provide load balancing. We needed to be able to provide encryption and authentication, and also not forget the webhook verification, which is where we all started. It's our bread and butter, and many folks are using it today. So we had to have these features in mind and make sure that those were part of the ngrok product itself before we could make it a Kubernetes Ingress controller. And if you remember from a few slides ago, we talked about how ngrok worked, and it ran as an agent in the command line. So it's essentially running outside of your application. It's separate. It's pointing to the port that your application is running on, but it's still two separate things. So how do we get ngrok, the application, and embed it inside of an Ingress controller? So the controllers are written in Go, which coincidentally, so is ngrok. The CLI, running as an external process, needed to get inside of a Go application. So we had the idea of taking the concept, or taking the idea of ngrok and that functionality and bringing it into an SDK and combining them so that you can have ngrok inside of your Go application code. This was able to make a tighter relationship between the application and the Ingress it was needing to get out to the world. If you think about it, in Go, you have the net.listen API that essentially spins up a web server inside of a Go application. We took that same interface and decided, all right, so you return this object to create connectivity to a specific web server running locally. Well, let's take that object, and instead of creating a web server, we're going to create a tunnel connection with ngrok. So ngrok.listen is an object that allows you to dynamically spin up and spin down tunnels as needed. It allows you to have a high availability and uptime because it's running with your application. It's not a separate process now running in another terminal or another process outside of your application. It's actually running together with your application. It can react to Kubernetes events without having to tear things up or spin things up or tear things down. And it doesn't need to worry about an agent needing to entirely stop or start depending on what you were doing with your Ingress in your Ingress connectivity settings. So thinking back to that diagram, we had that diagram before where we had the two controllers and it providing connectivity to a cluster. We have our load balancer, we have our Nginx Ingress controller. But instead of those, you now have a solution where you have a single Ingress controller that gives you access to load balancing, to encryption, to auth, to verifying webhooks. All of those things are in one place, and they're not tied to the environment where your Kubernetes cluster is running. They can be running locally on your box. It can be running in the cloud. It can be running on your own data center. And still, those settings remain the same. ngrok worries about the changes that happen behind the scenes, because those changes do happen behind the scenes, but all your traffic is being routed through ngrok, and ngrok takes care of all that. But remember also, we had that goal that not only we wanted to be able to provide Ingress to Kubernetes clusters, we wanted to seamlessly integrate to other objects inside of Kubernetes as well. So now, with things like Consul, you're able to integrate with Consul, because Consul and the Ingress controller for ngrok both use Helm. They both use a lot of the same things that are needed for the ecosystem to work well together. In fact, you only need these two lines in your pod annotations to get ngrok into a console service mesh. This shows the power of following community standards and playing nice in the ecosystem. And other Ingress controllers need to expose them out of the service mesh somehow at that point. But due to ngrok being able to create Ingress into any network and even service meshes, it just works when you put in these 2 lines inside of your service intentions. There's a few things that we want to share through our development journey that we recommend you keep an eye on and get an understanding of if you are looking into building your own Ingress controllers or just other controllers in general inside of Kubernetes. First is the controller runtime. This is the set of standard Go libraries that are used for building Kubernetes controllers, and it's maintained and used by the Kubernetes project team. You'll get to know these by also using the KubeBuilder framework. The KubeBuilder framework is a launching point that really helped us in building our controller. It's used for building Kubernetes APIs using custom resource definitions, but then also provides those same framework benefits like providing logging, telemetry, things like that. And also it connects in with using the controller runtime. So keep KubeBuilder in mind if you're looking into building controllers, and then also the controller runtime. So one of the big trade-offs that we looked into and just discussed a lot was, do we make an Ingress controller or do we go with the next standard? The next standard inside of Kubernetes Ingress is something called the Gateway API spec. And the Gateway API spec is essentially a role-oriented API, and it is the standard going forward. However, there's a few reasons why we decided to go with an Ingress controller. The first is that it's the most widely used. If you look at the adoption rate, most users of Ingress in Kubernetes are using the Ingress controller specification and Ingress controllers, essentially, and not Gateway API spec. It's commonly already known. People know how to use it. They know how to configure with it. It's something that not only do we know, but also the industry knows. And so we wanted to introduce our new controller to a known way of doing things. That way folks can learn us, and then as they move forward and as we move forward, we'll do the Gateway API in the future. Internally, it's what we use. When we set up Ingress inside of our own clusters, we're using the Ingress controller specification. Also, if you look at most of the gateway implementations, most of them are still in alpha, except for Hashi. High five to you at Hashi. Well done on getting yours out and outside of alpha. I think it's even outside of beta, so well done. But we figured if you look at all of those, it's okay that we went with something known first, and then going forward, we'll adopt the Gateway API. The Gateway API specs, as far as we understand, are still in flux as well. So it's a kind of a moving target. I know that the target is probably slowing down, but at this moment in time, we're still looking at the Gateway API spec and making sure that that settles down first before we develop our own. In addition to it being the standard going forward, what we are excited about with the Gateway API spec is the fact that it supports more than just HTTP and HTTPS traffic. We'd really be nice to have TCP traffic coming through with all the different types of network traffic that ngrok can handle. It'd be great to be able to also provide that ingress into clusters as well. As mentioned, it's the standard going forward. And also, as one of my engineers put it, it's everything Ingress is, just better. So the current status of the project is we recently, within the last few weeks, were able to go live with our general availability 1.0 version of our Ingress controller. We're super excited. And so internally, we're able to dog food it for using with our internal infrastructure cluster, our CI/CD processes, GitHub auth, our OIDC stuff, and also with Athens. Athens is a Go module proxy cache that serves all of our CI and local builds and passes. And so if it goes down, our whole CI goes down. And so that is essentially handling 80,000 requests a day. And that's all coming through our Ingress controller as well. And that's handling perfectly. So we love it. What's next in the project, as mentioned, is we are looking forward to adopting the Gateway API spec. That's the future. It's definitely somewhere where we want to go. We just wanted to start with established specifications first, and then go into the future specifications. Some of the resources that you would find helpful are here. I highly recommend looking at the Ingress to services in a console service mesh on Kubernetes. That's our integration guide with integrating with console. But also you have documentation on our Ingress controller, also the just general concepts of Kubernetes Ingress in general, and then the API gateway as well. Thank you all for listening. My name's Scott McAllister, developer advocate at ngrok. We'll be happy to continue the conversation about this or anything else you want to talk about. Just you can find me on one of these wonderful social media apps. Thanks.
Thanks so much, Scott. That was really great because it wasn't just a, hey, here we're going to tinker and how to set something up. Gave us a lot of the context, clarified the whole problem space, and gave us another option for ingress into Kubernetes, which you're going to need, to the point where I remember when I first started, it was like, why isn't this just like, more decisive and decided upon? There's so many different ways to go about doing it. And it's been a while since I've used ngrok, because my last foray into it back when I was doing software was for development purposes, just testing certain environments. But I loved the experience, so I'm glad to see that getting brought into Kubernetes. All right, so we've got one more talk on the horizon, but before we get into that, I did want to remind everyone that we are giving away a complimentary pass. By complimentary, I mean free. And 3 discounted passes to HashiConf on October. That's going to take place between October 10th through 12th in San Francisco, California. You get to come out and spend time with all your great community members in HashiCorp. And how do you win? Well, make sure that you check out the link right below my big head here at hashi.co. Build a giveaway, and make sure that you're registered for HashiTalks Build, because you have to be in order to be eligible for that giveaway. So check that out. So moving on to our last talk today, day 1 HashiTalks Build. We're going to be hearing about building Vault plugins with Christopher here, and not only how to build Vault plugins, but also how they work under the hood. So when you're ready, Christopher, take it away.
My name is Christopher Swenson. I'm an engineer on the Vault team at HashiCorp, and I'm here to talk about building Vault plugins. A quick outline, I wanted to talk a little bit about why we were doing this, a bit about how these plugins work under the hood using Go plugin, and then I'll dive into the main topics, which include talking about different Vault plugin types, and then how Vault plugins work in general. Talk about the plugin lifecycle, and then go into a bunch of best practices and show some example code on how to build your own plugins. So what is this about? This is about building plugins for HashiCorp Vault. The reason you might want to do this is that Vault supports a bunch of external systems out of the box, things like AWS and Google and Azure, but obviously can't integrate with everything. So you may need to build your own plugin to integrate with another system that you care about, like a system that you work with. Or maybe you need some capabilities that aren't possible with the base Vault, like using CGO to access C libraries for an external system. Or maybe you want to make changes to an existing plugin to add functionality that you care about. And just before we get into too much about Vault specific stuff, I wanted to discuss a little bit about plugins under the hood. So Vault is built in Go, and Vault plugins are all based on Go plugin. Basically, Go plugin works by separating out a plugin into its own binary, so that means it runs its own main function. This allows it to have much stronger independence from the main Vault binary. So Vault itself, whatever the prepackaged code is, but you can provide your own plugins that can do various tasks. And they don't have to be built into Vault at compile time. They can be specified at runtime, and they're run as their own separate binaries. They communicate over RPC. This means that there's no dynamic linking required. So we'll quickly go over how Go plugin works. It kind of elaborates on what I just sort of talked about. But basically, whenever Vault wants to load a plugin, your program, in this case Vault, it starts up a Go plugin client. And this has to specify the location of the plugin executable. So this will be the location of your plugin binary. And then that goes ahead and starts up the plugin in a separate process. That plugin is expected to start up the Go plugin server. And the Go plugin server does a bunch of initialization. And then it writes to standard out saying, this is the version I support, here's the protocol, here's how to contact me for gRPC purposes or netRPC purposes, and then maybe a certificate about how to securely communicate with it. And now the client has enough information from that standard out line to connect to the server that the plugin is running. And so now they can start communicating over RPC using either netRPC or gRPC. Generally, this is going to happen over a Unix domain socket, this connection that they establish, but it can also use TCP for systems like Windows that don't support Unix domain sockets as easily. I just wanted to run through a quick code example. I like seeing things in code to see exactly what's going on so that there's no magic happening here. This is what any kind of Go plugin main is going to look like. So this is not Vault specific, but you have basically the core of it really is this plugin.serve. So Go plugin.serve, and you tell it what you're going to serve. It needs a handshake config. This just tells it how to identify itself essentially with that it knows it's running in the correct environment, that it's your system that's asking it to run. You're going to specify what plugins that you're going to provide implementations of. This means basically what protocols are you going to support? I'm going to implement a particular plugin for Vault. What are all the names of them going to be? And then that needs to point to some sort of implementation that tells it how to run those methods. And then a gRPC server in this case, since we want to communicate over gRPC. On the other side, the program that wants to load a plugin, in this case something like Vault, the way it would start that process is it creates a client. And it says, again, this handshake config, this says I'm going to set basically things like certain environment variables so that the plugin knows that I'm the one talking to it. What plugins I want to be able to fetch from that plugin. Maybe it contains multiple implementations or multiple plugins. How to find the executable itself. So typically this is just location of the binary. But maybe you have some sort of wrappers for various other ways to access it or load it. And then any protocols allowed, meaning netRPC or gRPC. Generally, we use, again, gRPC. So after you've created the client, you start it up, and then you ask it to dispense the actual implementation that you're interested in, the actual plugin. And then now you can basically cast that to the plugin interface that you want and start accessing its methods, and then those will be transparently called over gRPC. And it's mostly as simple as that. There's a few pieces that we're not delving into, like the specifics on how these plugin interfaces work, but they work in a rather standard way. Now getting into Vault specifics, Vault is built on this entire framework, but it provides a bunch of interfaces and helper structs to make this a little bit easier, so you don't have to worry too much about these details like handshakes and this plugin map and things like that. For the most part, you can just build with this sort of template in mind, and Vault will know how to use your plugin already. A fun fact is that Vault is itself using all of these plugins internally as well as externally to provide most of its capabilities. So Vault itself, has a core set of capabilities around things like leases and policies, but most of the functionality that talks to external systems or provides storage and things is often built on this plugin system. There are 3 plugin types, and we'll talk about each of them. There are secrets engines, and I'll go into the differences in just a second, auth methods, and then database plugins. So secrets engines are the most general type of plugin, and these are typically used to either store information or generate secret information. So Yeah, static secrets, typically things that are stored and live a long time, or dynamic secrets are more short-lived things. So I'll give some quick examples. We have the KV secrets engine is probably one of our most popular ones, and it is implemented as a plugin secret engine. And this just provides generic object storage, essentially, that can be used to store secrets as just arbitrary JSON objects. The secrets engine can also be used to generate dynamic AWS access keys, for instance. So if you have an AWS role, you can load in enough information into the Vault secrets AWS plugin and have it generate access keys that are short-lived. You can also have, you can use the PKI secrets engine to generate entire PKI infrastructure like CAs and certificates. So really, secrets engines they're really very generic, but they're meant to store secrets or generate secrets and return them. The other plugin type you see most often probably is an auth method. And an auth method is designed to allow Vault to be able to validate third-party credentials. So essentially, they turn external credentials, like AWS credentials, for instance, into Vault tokens that can then be used to access the Vault API. This means that you can have someone authenticate, say, they're a program running on an AWS instance, and they can access the AWS IAM instance profile, call out to Vault, and turn their IAM profile into a Vault token that they can then, say, access some secrets that are stored in Vault. Ditto Kubernetes, you can have, say, a Kubernetes service account that has access to Vault, things stored in Vault, and we would use the Vault plugin auth Kubernetes plugin to turn those service account tokens into Vault tokens, which can then access Vault resources. JOT and OIDC is another very popular auth method. So you can basically take any JOT and specify, what it looks like and where it comes from, and be able to turn those into Vault tokens. Keep in mind that whenever we talk about secret engines and auth methods, the kind of key flow is that auth methods, again, is something that takes a credential. So you make an API call, here's my credential, and the auth method has some way of validating that and returning a Vault token. And a secret engine, on the other hand, though, takes that Vault token with standard Vault API call with that token as say, a header, and then it can return a secret or store a secret or delete a secret or whatever. But generally, it turns tokens into secrets, whereas the auth method turns credentials, external credentials, into tokens. The third kind of plugin that we see a lot is database plugins. So these are used in turn with the database secrets engine. So this is a super secrets engine that's built into Vault. And this allows you to work in a slightly different way than the previous ones do. They turn Vault tokens into database credentials. So it's basically a special type of secret engine where the secrets are going to be database credentials that are returned. And so it standardizes a lot of the logic inside this database secrets engine so that you can write a much simpler plugin that does all of the Vaulty stuff already, since it's basically the same for almost every database. You'd want to have the same sort of Vault logic, and you want to basically just plug in, okay, here's how to create a user, here's how to delete a user. So let's get a little bit into the mechanics of plugins themselves. So if you want to use a plugin in Vault, it's relatively straightforward. It has a few steps. The first is that you have to tell Vault how to find the plugins. So this means it has to be started with a plugin dir argument, or as part of its configuration, there's a plugin directory in the config, the HCL config. Once that's started up, you can copy the plugin and set permissions into that directory. So copy your plugin binary into that directory, and then set any permissions to make sure that the Vault user can read it. Once the plugin is ready and Vault is running, you can register the plugin. So this requires you to specify the plugin type, like secret or auth, and then your plugin, so the actual plugin binary inside that plugin directory specified earlier. And you do have to specify the SHA-256 of the plugin, just so that We know that nothing weird is going on where you're trying to register a plugin, but somehow it's been swapped out under the hood with a malicious plugin. So you have to acknowledge via the SHA-256 that this is the plugin that I want to register. And then once it's registered, this only has to happen one time, and then you can use the plugin a bunch of times and mount it a bunch of times inside Vault using Vault Secrets Enable or Vault Auth Enable. Are the two primary ways for secrets engine and auth methods. So this way you can, register my KV plugin, for instance, and then enable it at a bunch of separate paths. And maybe those paths have, different permissions. They'll all have different storage under the hood. With a database plugin, that has to be done in a slightly separate way by you would have to have already done Vault Secret Enable Database to enable the database plugin. The main database plugin, that is, and then your individual plugin will be used when you write a configuration to the database system and say, I want to use my plugin with this particular configuration to access, like, say, a MySQL database or an Oracle database. If that seems like a lot, sometimes when you're doing development, you don't want to necessarily go through all of this, and you can use Vault Server dev plugin dir. And dev plugin dir allows you to specify that everything in this directory is going to be plugins and go ahead and just automatically register them whenever Vault starts up. So this allows you to sort of skip this step. It just reduces a little bit of the toil whenever booting up Vault and doing a bunch of plugin testing. So nice, handy method there that we use when developing plugins. So let's talk about plugins themselves. So like, what does a plugin look like code-wise? So typically we like to structure ours this way. This isn't, there's no hard and fast rules to how it looks. As long as you have a plugin main that looks kind of how we're going to show, then it will work. But in general, we like to put our main inside a CMD folder. And this is a sort of standard Go practice for how you, where you put your main functions. But we want to say the main goes in there and that only contains the main. Typically, you'll have the backend for your plugin, the actual piece that has all the storage and does all the work inside of backend.go, and then any individual paths that you expose for the plugin, like API paths that people can call, will be listed under path underscore and then whatever operation that is. In general, the logical.backend plugin interface is the key Vault plugin interface that everything has to follow. But we fortunately don't have to work with this directly too often. Most of our plugins, I think every single one of our plugins uses a higher level abstraction over this, which I'll talk about shortly. But technically, under the hood, every Vault plugin looks like this. It has some initialization stuff that happens over here on this left path. But for the most part, whenever almost all of the work is done in these three methods here: handle request, invalidate key, and handle existence check. And those handle all of the HTTP requests for your plugin and do most of the work. But this is a little abstract and it's a little low level in terms of HTTP, so you're handling like raw requests there. So in general, we typically use the SDK framework. So rather than having to work with logical.backend itself and having to deal with all of this plumbing ourselves, if you use SDK framework.backend, this is a struct that you can mix into your plugin and have it handle all of the HTTP logic for you, so that you can use a more path-oriented way. So saying, instead of handle this HTTP request and have to parse it yourself, you say any HTTP request that comes in this path, which maybe has regular expressions and whatnot on it, I want to map it to this Go function. And then the framework.backend core will sort of handle all the HTTP routing. So what does a plugin typically look like in Vault? It's sort of built on what we saw earlier, but it's a little more specialized to Vault. So our main typically calls plugin.serveMultiplex. This is a Go plugin method. And I'll talk a little bit about multiplexing in a bit. And this has to map to a factory function. And the factory function typically just creates your plugin. So it does whatever initialization is needed to create an instance of your plugin specifically. And then that usually will boot up a framework.backend, initialize that, and call setup. So, and then this is where, whenever creating that framework.backend is when your plugin sets all the paths that it's going to respond to, any like cleanup functions, any help. So if you're going to show any like help text when someone queries about your plugin, you put it there. And then after the factory like creates your plugin, the initialization function is called, if there is one. And then you go into your main loop, and this is where requests are basically just handled automatically by the framework.backend. Each request will then be passed to the correct path in your plugin and calls the appropriate go function. If you have a periodic func, that will also be called occasionally. So this is where you can do like any cleanup work that your plugin might need, or maybe you need like to do some maintenance on like your storage and whatnot. That would be done through a periodic func. And then finally, when the plugin is shut down, the clean function will be called. So this typically looks something like this for the main. You have this sort of just generic setup for doing some flag parsing. You call plugin.serveMultiplex, like we mentioned before, and tell it where to find new instances of your plugin. And that's it. Really, the core differentiator between all plugins is this line right here that says this plugin uses this factory. This factory, like I said, is the main differentiator between different kinds of functions, and it basically is any function that can return a logical.backend. But they typically have a sort of standard structure to them, at least in our plugins. So first off, we're going to want to be returning our backend for the plugin, meaning the actual plugin itself that does all of the work. And so our factory function typically is as simple as go ahead and create one of these backends, populate the framework.backend with some information, things like what kind of plugin type am I? Logical means secrets engine in this case. What kind of help am I going to be providing? Like, help text for people who might be requesting more information about your plugin. And then really the key is the paths. So this just says this is a list of all the paths for every operation that I'm going to be providing. And we typically specify those separately in separate functions, since they tend to go into a lot of details about all the parameters and path arguments and whatnot. It's important we call setup before returning. This is just an implementation quirk that the factory is responsible for calling setup, and then we return. And that's really the core of it. Any other initialization you want to do would happen here if you needed to, set up some keys, or maybe initiate communication with some other system if you have enough information to do that. One key point here that I wanted to mention is typically when you're working with inside the factory and inside the setup, you do get access to storage, meaning you get a view into Vault storage to do some initialization if you need to, and that will give you a storage view implementation to do that. But you don't want to save that. So in general, that storage view is not going to be valid after this finishes up. And so it's dangerous to hold on to that and try to do things on your own behind the scenes, for instance. That's what the periodic func is called. I mentioned this earlier, but essentially you can say every now and then I need to do some periodic work. That will allow you to access storage through the request it passes in. So that way you don't need to hold on to the storage view from the factory or the setup methods. You can use the periodic func to do any cleanup or other maintenance you need to do. So the actual paths themselves, these are the pieces that implement any endpoints that your plugin is going to let people use. These are all exposed through framework.paths, and they're given back again in the factory in this part here. So each of these goes into basically a bunch of details about what kind of pattern are we going to match. So what does the path look like? In this case, maybe it's something as simple as config/keys, but if you had maybe multiple keys and you wanted to use a regular expression, you can add that here. Framework even has some additional methods you can call that help you sort of build these strings. Fields are anything that you want to allow as in the request. So if the request has some certain input that's required, you can specify what that input looks like here. And then you specify what the actual operations are. So anytime I get a read, call this method. And you can specify some additional information about like what parameters you might return and what those look like as well here. But the key really here is pattern here, and then operation, go function. The actual framework operation itself is just kind of straightforward Go code. It needs to be a function that takes in a context and a request and returns any kind of data. This will be serialized to the user and an error, of course. And these typically in plugins follow a sort of standard pattern for a read. Grab something from storage related to the request. Also worth noting, as a convention, any data in Vault storage is JSON encoded. This isn't a strict requirement, but we usually follow this pattern. So typically, anytime you fetch anything from storage, you immediately decode it as JSON. And maybe you do some other manipulations or generate new data, and then finally return that to the user. And then this will get serialized to the user as JSON as well. Replication. Luckily, so since Vault does have high availability and can be running, a complex cluster, you need to worry a little bit about replication. Luckily, this is mostly handled for you when you use the SDK framework.backend. But there is a key that you do need to implement. If an error does occur and storage has to be rolled back for some reason, it will call the wall rollback function, the write ahead log rollback function. And this will give you information about any data that was rolled back. So if you, say, need to synchronize with an external system to delete a user that was created as side effect, then you can do that in your wall rollback func. And there's some tuning parameters you can provide about how often this occurs or what the timeouts are and things like that. Roles. So here's an interesting thing. If you've played around with the Vault, you've probably seen roles pop up a lot. Interestingly, Vault itself doesn't have an internal concept of a role. It only has policies. And plugins define what roles mean to them. We have some kind of loose guidelines that about what roles mean in various contexts. So, for example, if you're an auth method, then the Vault role is typically mapped to the auth method's credentials, and then that's mapped to policies that they allow the use of. This way you have essentially a layer of indirection and making it use RBAC, so role-based access control. So this way your credentials aren't mapped directly to the policies, they're mapped through these roles. And allows you to modify the roles independently, and then this way they're not so tightly mapped. It makes it just in general a lot easier to work with. On the other hand, for a secrets engine, this might mean the Vault roles are mapped to, say, AWS credentials generated for that. So you set up a role in the AWS plugin and have that, say, mapped to a set of credentials, and you might have access to that role to generate those credentials. So it sort of flips that on its head a little bit. And sometimes they're used in just totally different ways, like in KMIP, the KMIP secrets engine, which is used for certain other kinds of interoperability with other systems. The roles are mapped to a certificate key pair, so used to authenticate, and that is mapped to a scope, which essentially is just like an isolated chunk of that KMIP instance for storage. So not really quite in the traditional policies sense, but it has its own kind of concept of roles. So it's up to your plugin what roles mean to you, but it's probably for the best and will confuse users the least if they sort of map to, say, how the standard plugins use roles and have similar methods. So I definitely encourage you to sort of work with those as closely as possible. Policies. Typically, the policies are not explicitly set or used by plugins, but you use them to access the plugin endpoints themselves. So any of those endpoints that you expose via your framework paths, the user needs to have access to those. And so policies are still are used by Vault to enforce that. So these are just the standard Vault policies, checked against the auth token of whoever is calling that API endpoint. The sort of exception is the Vault auth methods can cause tokens to be issued, against roles and therefore policies, and then those are bound to those policies. So since they can generate Vault tokens, they do interact with policies a little bit more. Multiplexing. So I didn't talk about this too much, but you might have noticed we were using serve multiplex. You can just use serve instead. The key is if you use serve multiplex, Vault will try to use a single instance of the plugin per namespace instead of multiple ones if you mount it multiple times. This can have a bunch of benefits if you're running only a single instance. Notably, if you're running hundreds of mounts of this plugin, like for say a very large deployment, hundreds or thousands of them, or hundreds, then that will save you a ton of memory and a ton of process space. So where you're running only a single instance instead of multiple, and also can just in general make things more efficient. We do know that there are some cases where you just really want to have that extra process isolation. So serve is still supported, but definitely we encourage serve multiplex by default. I want to wrap up with a few just best practices, for writing your own plugins. The first best practice is, of course, to look at existing plugins to see what they're doing. The HashiCorp plugins, there's about 40 or 50 of them that you can look at. So a few quick examples of each are Vault plugin Secrets KV. This is sort of one of our gold standards, our most popular plugin. It's built into Vault, but it's developed in a separate repository that can also be used as a standard external plugin. The auth plugin example, unfortunately named that the auth plugin is swapped there for some reason, but it has just a very basic auth method that you can look at for inspiration. And then for a database plugin, you can look at one like, say, MongoDB Atlas, or even there's also an Oracle plugin and a bunch of others that are good ones to kind of model on how they structure their code and whatnot. And they don't actually follow all of the guidelines and structure that we mentioned before, but they do a pretty good job, and we've been working with them for many years and try to keep them up to date. So a few other tips: definitely use the initialize func and periodic func and close methods. Don't try to roll your own, cron-like functionality where you, say spin up go routines and sleep and stuff like that. You'll run into problems with the storage views maybe not being valid whenever you try to run later. So, and we really encourage using things like periodic func and initialize func to deal with any of that, to deal with any periodic maintenance needed or initialization. Again, use serve multiplex instead of serve. There's a bunch of helper functions in Framework that can help you do things like working with paths or building regular expressions and things like that. So definitely take a look around at what public API offerings there are in Framework, Vault SDK Framework, to sort of help you build your plugin. If you are developing a database plugin, it's important to use New Database Error Sanitizer middleware, a very, very long name, but basically it helps in case you accidentally log usernames and passwords that you're generating into your logs. It will help get rid of those. If you do have questions about this, I'm around after the event, though. You can use Discuss or to look at our normal Vault forum, or open up a GitHub issue on Vault or the individual plugin that you are having trouble with, and we'll be happy to engage with you. All right. Thank you very much.
Thank you so much, Christopher. That was an awesome talk in terms of Vault plugin development, being able to see both down into the code and what you should be looking for, as well as the general patterns, all of the different best practices, and just a lot of little tuning things like the whole multiplex concept and how you can just use one loaded plugin as opposed to many. I found that very, very interesting. So thank you so much for putting that together. And before we get into anything else, I do want to mention again, HashiConf, October 10th through 12th, 2023 in San Francisco. Registration is open. And since you're here with us today, we do have a giveaway of a pass and 3 discounted passes that you can check out at hashi.co/build giveaway. Cue banner thingy under me. Yeah, there we go. That you can do there. Make sure that to be eligible for that you've registered for HashiTalks build as well. And also, if you want to get more involved with the community, we do have our HashiCorp user groups, and you can check those out and join one in your local area at meetup.com/pro/hugs, like actual hug, but it stands for HashiCorp user group, and you all probably know that. Okay, so that wraps up day 1 of HashiTalks build. Thank you so much for joining us. We hope you enjoyed it. And hey, we've got another great day of content planned for you tomorrow. That's also starting at 10 p.m. Eastern. Continuing with our theme, we're going to have great talks on Terraform provider do's and don'ts, Nomad with machine learning, and more. So what did I 10 a.m. Eastern, not 10 p.m. Eastern. Sorry, it's early on the West Coast. So be sure to join us. And until tomorrow.